All right, yeah, it's cold in here. All right, how's everybody's lunch? Good?
Good.
Feel more awake? Ready to learn? All right, we're going to continue on. I haven't lost my voice yet. Fantastic. We're going to be talking about replicating natural biological processes, which is essentially what natural farming strives to do in an agricultural environment. Well, which one of these biological, or which ones of these biological processes does natural farming try to replicate? Well, I mentioned it earlier. The main one is forest floor dynamics. Also, we have microbial plant symbiosis. Mentioned that earlier. Natural process of biological equilibrium, where most biological environments have a set biological equilibrium. Basically means that there is a steady flow. It could be kind of a peaking and dropping or kind of steady, but either way there's a set of microorganisms that exist in this environment at an equilibrium state. Not one microorganism is going to be more powerful than one or a group of others. Powerful, that's a really bad word. Dominant. Natural diet. Well, we're talking about livestock. So when natural farming is incorporated into the livestock scheme, natural diet is one of those natural processes that's being replicated. Well, let's look at forest floor dynamics, which is the main one, as I mentioned. In a forest floor, there is certainly nutrient cycling. Nutrients. We're talking about plant nutrients here, mainly. And these will include, of course, the macronutrients being nitrogen, phosphorus, potassium, calcium, magnesium, sulfur. And then the micronutrients. I can list them all off, but you're not going to remember them anyway. Either way, that these are nutrients needed for plant development and plant health. Micronutrients only being called micronutrients because you need less of them than the macronutrients. They are just as important as the macronutrients. So don't think if you didn't have chlorine, your plants would do fine. No. It's the same as if you didn't have nitrogen. It needs all of the above in order to exist. Okay? Nutrient cycling, you have the nutrient cycle. We talked about this in class the other day, where you have decomposition, nitrogen gas, animals, pollution, people contributing to nitrogen going down, microorganisms contributing to gaseous nitrogen going out of the soil. It's a pretty dynamic system, the nitrogen cycling system. Of course, there's phosphorus and potassium. They all have their own cycles, which basically mean that they have their own set of biology that breaks down these materials, makes them plant available, gets them locked into soil sometimes, and there's a lot going on there. I did talk about that for about 2 hours the other day in my other class. So, nutrient cycling, everybody understands that nitrogen can be in a gaseous form, it can be in many different forms in the soil, but plants can only take up 3 different kinds. And phosphorus is really the same kind of thing. Phosphorus in the soil can only be taken up if the phosphorus is bonded with calcium, or at least a certain specific state. Most phosphorus in the soil is not plant uptakeable. It gets moved around in different phases, in different forms, sometimes running into a microorganism which puts it into the form that can be plant uptakeable. Calcium is the same way, magnesium is the same way. Different sets of microorganisms, different parent materials lead to these nutrients moving around in the soil. So with forest floor dynamics, what you're doing is you have natural biological, go ahead.
Okay, you're just talking about the forest, but I would imagine if man is in there, you would have a lot of deer, bears, squirrels.
So macroorganisms and their effluence is what you're doing.
Oh no, you cannot take one away from the other. It's all together, right?
Right. So you're going to have macroorganisms in your agriculture environment, just like you would in the forest floor. You might not have deer, but I can tell you what, a handful of worms makes a lot more poop than one deer. And if you can, have worms in abundance in your soil, then you're having the same effect as you have with the deer, but also aeration, a little bit microbial stuff going on. So yes, being that macroorganisms are generally the same, contributing to the same levels of nutrients in the soil. Okay? So yeah, nutrient cycling, basically, everybody got that? Organic matter. Leaves, where was I going to go? Oh, nutrient cycling. You're simulating nutrient cycling when you do conventional organic fertilizers, right? You're simulating the dropping and the release of these nutrients into the soil, which are generally already plant uptakeable. So you're simulating these nutrients available in the soil, which does not come in, when microorganisms generally don't come into play, because as soon as you take these fertilizers, they're already plant uptakeable. You're basically taking microorganisms out of the equation. The goal is to keep microorganisms as part of the nutrition cycle in natural farming. Okay? Organic matter, you got leaves, you got sticks, you got twigs, you got dead insects, and dead worms, and dead nematodes, and all kinds of organic matter. Mulching is a major part of natural farming. You'll see many times people mention they inoculate their field with IMO4. They don't talk about what they do next. Well, if you take microorganisms that aren't used to seeing the sun and high temperatures, and you inoculate it out into your surface soil, and you water it in, chances are after a few minutes drying out, your microorganisms are dead. So you need to add mulch in the time you're adding indigenous microorganisms, because you need to keep the sun away, and you want to keep the moisture levels high, and you want to add organic material. You got to make sure that this mulch is disease-free and from your own property and from your own plant tissue, but you need to use it. So when we're incorporating mulch into our system, we're incorporating this high levels of organic matter. So the guys that do taro natural farming, like John Caverly, John will, when he puts his taro in the hole, takes a nice puka, and he mulches literally a bowl of mulch around the base of the taro. And he almost 6, 7, 8 inches of mulch on his land. It's because he has so many and has added so many indigenous microorganisms that mulch, like within a couple weeks, just disappears. Or where does it go? It gets broken down by the indigenous microorganisms. Those are then plant available with the nutrients in which it breaks it down. So not only that, but IMO4 itself is just high in organic matter, being that it's a carbon-based source. So with natural farming comes organic matter. Everything's made of plants and animals. That's what the definition of organic matter is, plants and animal-based products. Okay? So with organic matter comes healthy soil aeration, great color, pH stability, all those things. We're also trying to simulate forest floor decomposition. Well, forest floor decomposition happens very, very, very quickly. Otherwise, the forest floor, as you know, would have a lot of matter sitting on the forest floor. As I was just saying, when John goes out and he puts out his mulch, that mulch gets decomposed really quickly. And that's because he has rapid decomposition. Why? Because he selected decomposers from the environment and put those in his soil. So we definitely have decomposition, which releases nutrients, causes aggregation, all these wonderful things going on to the soil because of decomposition. in areas in the forest floor where there's very little oxygen. So imagine under a tree which has got leaves on it and all that, there's certain areas in there where there's very little oxygen and anaerobic decomposition happens. Anaerobic decomposition typically involves fermentation. We talked a little bit about that earlier, fermentation being one of the main ways on which natural farmers access minerals from their materials. As a farmer, how am I going to get the phosphorus out of this plant material? Squeeze it out? Yeah, that kind of works. Might mix it with some water and have the phosphorus trickle out of that plant material? Yeah, that kind of works. Or how about I use osmotic pressure and I suck that material out using sugar or something like that. So fermentation is replicated with natural farming. In these areas with no air, you have anaerobic decomposition, which releases different kinds of nutrients into the environment. It enables the environment to hold different kinds of bacteria and fungi. Very heavy in the bacteria side. So if you have areas and pockets of the forest floor where fermentation happens, these are pockets of bacteria in which the rest of the soil environment can kind of feed from and use to increase its biodiversity. Got that? Retranslocation. Okay? Retranslocation. Translocation is nutrients going down and away out of the environment. What is retranslocation? It's having nutrients go down out of the root base of the plants, maybe down to the sea horizon of the soil, which is about halfway down to rock. And because of microorganism demand up top, these materials, these nutrients are actually pulled back into the environment and sustained at the forest floor. So this is very common to see in forest floors, retranslocation. It's kind of like this tiny little cycle going about 8 to 10 feet below the surface of the soil. The materials will go down and then microorganisms need them and then we'll bring them back up into the environment. So there's these nutrients cycling because the microbes are consuming them, breaking them down, they're breaking down each other, and those nutrients stay within this little system. Of course, there's a big heavy rain, what happens? It gets washed away, but not so much in forest floor. Because there's so much organic material, there's tree roots, there's so many things that will hold those microorganisms in that cycle. You can create a cycle like that in your agricultural field where you have retranslocation, you're doing natural farming right. You can almost stop adding amendments for whole seasons at a time. Of course, you have microbial reproduction, which creates biomass. We talked about how important that is, and enzymatic activity. So we're trying to, as a natural farmer, make an environment on which microbes can rapidly reproduce. And we're trying to make an environment that will entice macroorganisms like worms, birds, and such. Okay? So you see how forest floor dynamics works, and you see how that relates to natural farming. I could literally do a bullet point for natural farming on the same other side that has the same words. So I'm trying to do all of these things. Remember I talked about microbial plant symbiosis. Okay, so these are close associations, symbiosis, and mutualism. Close associations are when microbes and plants kind of use each other but never really come in contact. These are sometimes free-living microorganisms in the soil. Close association would be a nitrogen-feeding bacteria or fungi. A deer comes by and poops on the ground. The nitrogen-loving bacteria or fungi will break down that nitrogen source. Of course, when it does so, it might have some left over. Everybody, when they eat, they get a little piece in the side of their mouth and it skims off, right? Same type of thing. It'll release some of those nitrogen and it'll be taken up by the next door plant. Now that nitrogen-eating microorganism didn't really care about that plant. That plant had no idea that dude's over there, but there is certainly a close association, right? One wouldn't be there without the other, especially the plant associated with the one that breaks down the food. Okay, so then there's symbiosis. That is going to be where one benefits, we talked about this, one benefits in a close relationship, usually coming in contact with each other. And then we also talked about mutualists, and these are where both of them benefit from the relationship. There's also several that it's not just two, it's sometimes 3 or 4 organisms all together are all mutualists together. So we're trying to recreate microbial plant symbiosis in natural farming. Okay, we know we could do this by exosymbiosis, meaning that we can deal with exophytes, right? Ones that are microorganisms on the outside of the plant, because we can see them, feel them, move them around. The endosymbiosis, that's still a little tricky. We're literally in the pioneering phase of these studies, and scientists have told me there's no reason to not think that when I take fermented plant juices from one plant and I inoculate another plant with those fermented plant juices, that there is some sort of mycorrhizae or fungi or endobacteria that goes into the stomata of the other plant and goes in. It's just that we don't know enough about it, okay? They're telling me it, in my own belief, I think that that happens, but there's no scientific data showing so. As far as we know, all plants get their endophytic microorganisms from their parents. We don't know if they get it from the soil or where they, we just don't know. But we're hoping to create an environment where the plant is so healthy, and we're hoping to have plants that are already inoculated with these endosymbiosis. How do you do that? Well, you use the same genetics, and you start seed saving, which is actually an important part of natural farming and such, okay? We have mycorrhizae relationships. Remember I mentioned that. So that's going to be the fungi that goes to the roots and does an exchange of sugars for nutrients and water. Remember I said that all plants have some sort of relationship. We're trying to replicate this type of biological process. And how do we do that? Well, we make our soil so biologically diverse that we can pretty much guarantee that if a plant goes in there, it's going to have a mycorrhizal relationship waiting for it. That's as far as we can take it. We don't know. We don't know. Nobody's looking at the species that are in there. So once we start identifying species, we can make some more bolder statements about this stuff. We're trying to simulate the production of growth-promoting plant hormones. Okay. What are growth-promoting plant hormones? Well, all hormones are growth-promoting. When I was 17 years old, zit-faced, skinny kid, couldn't get a date for his life. Much different than the specimen you see before you today.
Transformation.
The transformation, right? Yeah, still a loser. But what I'm trying to say is, as I get older and as I go through menopause, yeah, right. No, as I get older and as I become a different person, essentially hormones in your body go through different phases. Okay, it's kind of naive to think that that doesn't happen for plants, so it certainly does for plants. There's a few ways that plants can get plant growth hormones. They can produce them themselves, which is when they produce cytokinin, oxygen, gibberellic acid, and they make their own hormones. Sometimes there are microorganisms that can stimulate the production of these plant growth hormones, which are generally beneficials. Remember that, where I mentioned, what's it called? Brain fart. The thing earlier, resistance, acquired resistance, yeah. So when some microorganisms do the acquired resistance, it causes the production of plant growth hormones. Or plants can just be inoculated with these. We've been able to, as humans, synthetically make auxin, which is a growth hormone, and spray it onto plant roots and have it taken up through the water, and then it behaves just as if it was produced itself. Okay? So, wouldn't it be ideal in a natural farming environment to have one, free living microorganisms in plenty that will cause this reaction in your plants, and then also having plants healthy enough to produce their own? When you have high levels of hormones, you have big yield. When you have high levels of hormones, you have a healthy plant, you have no disease, you can fight off pests. What's really key to growth and the health of your plants is these PGRs, plant growth hormones or regulators. Okay? These, as I said, can improve or aid in plant defense through that systemic resistance, causing these plant growth hormones, as I had mentioned before when we saw the video, there are some bacteria will just prevent pathogens from entering because it doesn't want it in there. Why would you let something in that's going to ruin your house and burn your house down? You're going to defend it to the day they die, right? So that's essentially what we're trying to do, is improve or aid in plant defense. Any questions? Remember I said ecological balance? This is a real thing, folks. It's in your biology books. Defined as a state of dynamic equilibrium within a community of organisms in which genetic, species, and ecosystem diversity remain relatively stable, subject to gradual changes through natural succession. So basically there is a set of microorganisms in a certain population. They have certain functions and they are all kosher with everybody in the group until there is an environmental change or a gradual change through natural succession. So if over time a forest consumes all of the nitrogen in the environment, the equilibrium will change after a while because there won't be as many trees, and then all of a sudden you move to shrubs, and then you have grasses in the area. Sure, it's a natural progression. It happens all the time, but you're still, throughout the whole time, you're going to have this kind of steady equilibrium. And then also, it's a stable balance in the numbers of each species in an ecosystem. It's kind of a naive definition, but it is a definition. Because sometimes there are species that are different species, but they have the same function. And if one substitutes for the other, what's the difference, right? Okay. But farmers must realize that there is no mention of him or her in this definition. Quit thinking like a human being. You have nothing to do with ecological balance. You are the reason why we came up with the definition. It's because we make things unbalanced. So we must realize that if we're going to incorporate ecological balance into our agriculture system, we need to be as far away from that system as possible. But it's an ag system, so it's tricky, right? Getting out there and touching everything every day is not going to help. But setting a framework for decomposition and plant growth hormone production, all these things, and sitting back and building the framework is essentially what you're playing God in your own little area, right? But you're not going to be a dominant God. You're an all-inclusive hippie God, just everybody together, you know? Okay. Only thing the farmer can do is lay the framework in the process. That's a natural farmer. Realizes that there's natural processes going on, and all he or she can do is lay the framework. Cannot dictate what goes on out there. If all of a sudden they lay the framework and all of a sudden they have an aphid infestation, well, how are your microbes? Okay, fine, we address that, and then now we can deal with the aphids. But let's look at the fact that let's do a soil test, let's do a respiration test, and I bet you that if you have a higher soil respiration, more microbial biomass, your aphid problem will probably be a lot less. But by the time you see the aphids, it's too late, right? Because the whole system has been thrown up. We need to figure out how to rebalance that system. That's a natural farming standpoint. How can I rebalance the system? Not what can I put out there to get rid of the aphids. Okay? Sometimes it takes, wipe out your yield. Sometimes your whole field could be taken out, but you're not spraying chemicals. It's a risk you take, but you just have to do it correctly. And of course, simulating natural diet. That's one happy pig. Replicating a diet more like natural diet of the animal. Hey, imagine that. So what do pigs eat in nature? Right? What do wild pigs eat when they go out?
They graze.
Yeah, they eat fruits. Lots of fruits. They eat roots. They eat insects. What else?
Grass.
Fermented organic material. Live greenery. What would be so bad about feeding a pig those 5 things? Right? Well, because it takes time and effort to go collect it. Now, a natural farmer is willing to trade time and effort for money and health and the wellness of his or her pig. Most important in that diet, fungi. Great source of nutrition for pigs in nature. Pigs have this amazing sensory organ right here. They can smell which ones are down there. If they know if they've tasted this root fungi before, if they smell it, they'll get down there and they'll eat it again. Well, when a wild animal finds something delicious, what does that mean? It means it's good for them and it's something that they should naturally eat, right? So if you see pigs that are digging out your yard and going for all of your roots, it's because you have tasty roots. So, most importantly, if I can make a feed and an environment for my livestock which are rich in microorganisms, I'm going to have a happier pig, my meat is better, less disease, and faster growth. This has been proven. Probiotics stimulate immune system and increase nutritional breakdown and absorption. Why not have some sort of probiotic in your food, more or less your pig's food? Who here is not taking probiotics? Everybody here is taking probiotics.
You mean like fish oil?
No, that's just a nutrient. I'm talking about ingesting microorganisms on a daily basis to improve your gut health. Anybody? I am. I take lactic acid bacteria every day. Why? Because it's the main probiotic in your gut. And so I supplement it. Why? Because I eat junky food sometimes. But the point is, probiotics stimulate immune system. As long as I've been putting probiotics in my system, I haven't got sick once. I swear by it. Increased nutritional breakdown. Well, it's naive to think that we break down our food. Okay? We have nothing to do with that. What we do is create an environment so that microorganisms in our gut can break down our food for us. And as long as we have a healthy environment, we have a healthy digestive system. If you are giving your pigs corn, which has been sterilized and steamed, are you giving your pigs any microbial nutritional health, any probiotic health? Oh, wait, my feed says probiotic on the side. So wait, they inoculate it with 2 different kinds of probiotics. What about the 1,500 other kinds that are naturally in the gut of the pig? If I hand that pig a handful of forest soil from my nearby environment and it just barely inoculate his gut with those microorganisms, be better off than just handing him 2 probiotics that come inside. So, natural diet, super important, especially when we talk about pigs, chickens, cows, the whole thing. Okay? I'm going to have to plug this puppy in here. Give me 1 second, I'm running out of power. Of course. Good? All right, let's let's talk a little bit about the materials. We've come to the exciting part. We're done with the sciencey part, but you guys do realize that this is right now is where most natural farming classes start. Is right now, okay? Without any background of microorganisms or biology or anything like that. So let's pick it up where most start. We're going to talk about several of these amendments. I'm not going to say how to make them. I'm going to say what they are and why they're used. And then if we get to the video, you can watch how we make it, or please come to the next class. Okay? Well, remember I said there's two categories. We got our fermented plant-based materials, and then we have our fermented animal-based materials. Starting with the plant-based materials first. Well, we have fermented plant and fruit juices, sometimes called FBJ. The guys who started this whole thing really love their acronyms. I find that to be confusing. I call it plant food, because that's what it is. It's a foliar nutritional supplement and microbial inoculant. And then also we have IMO4, which is what most people identify natural farming with, and it's a soil inoculant. What does that mean, soil inoculant? Soil additive? It's a biological booster. That's probably the best definition, I'd say. Additive could be lime, could be nitrogen. I'd say focusing on the biology, yeah. Fermented plant juices. I call it plant food. Just like the name says, it's fermented plant material. Remember how I said, how am I going to get the phosphorus out of this material? Squeeze it, stomp on it, press it? What? No, I use osmotic pressure. That's what we use in natural farming. Osmotic pressure, let's see if I can bring this up. Is there a link? No. I have a video. Example of osmotic pressure in the kitchen. Well, let's first of all, before we go there, define osmotic pressure. Osmotic pressure, or osmotic movement, is the movement of a material, whatever it is, through a semi-permeable layer from an area of high pressure to an area of low pressure. Okay? To give you application in that definition, semi-permeable layer would be a cell wall. Okay, to give you application. So it's the movement of material through a cell wall from an area of high pressure to an area of low pressure. So if we're talking about water's osmotic pressure, we're talking about, imagine an area on one side of a cell that has less water than an area on another side of the cell that has water. What will happen through osmosis? What will happen is an equilibrium will establish. Water will transfer through a semi-permeable layer until it's even pressure on both sides. Okay? Here's an example of this. You have a dried up lettuce leaf. Let it sit in water over a short period of time, and you'll observe osmotic pressure. So you have this in the bottom of your fridge. Everybody always throws them away. Don't throw that away. All you need is 3 hours and 35 minutes. And what's happening here? The molecules, the water molecules, are passing through one at a time through the cell walls. It's being absorbed into the plant tissue. The cells are elongated and then filled with water, and then that's osmotic pressure. Eventually there's an equilibrium on the outside of the bowl and on the inside of the cells. It's exactly what happens when we make fermented plant juices and we use sugar. Let me explain. Plant material. I'm going to make fermented plant juices. Okay? There's many different ways. You can use specific plants to make your fermented plant juices. You can use a variety of different kinds of plants based upon the way they do things, like their rate of growth or their ability to defend against pathogens or whatever. So you could probably do a general kind, or you could do a plant-specific kind. Let me explain the difference. So, plant-specific kind. If I am growing tomatoes, and my tomato plants are just about to go into flower, well, I can tell that because they start getting a little bit of elongation, they're starting to stretch, the nodes are differentiating a little bit, which is making room for the little fluorescence that come out of the stem. And as a tomato farmer, I know that the biggest, best, most marketable fruit comes from the main apical stem. And when you get other shoots coming off, it actually robs that main apical stem of the health of the plant, which is why most commercial tomato farmers will cut off all of the suckers. Because they know the main growth happens up there, and they can get a better fruit and more yield at a better price. So what do they do with those suckers that are on the side? Well, a natural farmer would take off those suckers, put it into a bucket, mix it 1-to-1 by weight with brown sugar. Never white sugar. Why? Because it has been blasted with all kinds of chemicals that kill microorganisms. Brown sugar, not having those, mixing it 1-to-1 by weight. And what happens? Well, the same kind of thing we just saw, but in reverse. The sugar has a much lower pressure than the water that is on the inside of the cell of these suckers, of the branches, and the leaves. So eventually osmotic pressure will cause an equilibrium. The sugar, lower pressure side, will suck the water and what comes with it. Some plant nutrients, plant hormones, and possibly some endophytic fungi or bacteria get pulled through the permeable layer and out into the environment, into the sugar. Eventually, once there's an equilibrium of water on the outside, water on the inside, that will cease. Right? That's using osmotic pressure, and that's when we ferment plant juices what occurs. The first couple days, the sugar is pulling out these materials. So if I put these materials in for a 1-to-1 ratio of sugar, and I wait 7 days, the first couple days, the sugars, or the water and the nutrients are being sucked out, and eventually it reaches an equilibrium by the second or third day. Okay? Then, we allow it to sit for 4 or 5 more days. What are we doing then? Well, we've already extracted the nutrients out of it. What we're doing is creating an anaerobic condition, an area where there's very little air, because this is a very soupy kind of viscous material. And plant pathogens, these pathogens that cause disease on plants, generally can't exist outside the plant environment in areas of low oxygen for very long. Also, fermentation, the sugars that are in there, the simple sugars, glucose, start getting turned into alcohols. Alcohol then kills off several of the pathogenic microorganisms that might still exist in that material. Okay, so we've just created 2 ways for pathogens to be killed in this material, leaving only microorganisms that are big enough, strong enough, healthy enough to withstand alcohol and anaerobic conditions. These might not benefit plants, but if you put them into the soil or on the plant surface, you're going to have that type of mass action. They may not do anything, but they take up space where pathogens can exist. Okay? So, 7 days later, I took my suckers and I did my little fermentation, and I have this material that I strain out. We'll go over it in the movie, but you'll see that this material has plant hormones in it, right? It actually has the same level of hormones that the plant had when you cut it. And if you know that the plant was just about to go into flower, you know that there's a transition. There's a sudden flush of maybe cytokinin and a reduction in oxygen, because you don't want so much growth, but we're looking for flowering. It's going into a different phase. It's a teenager becoming a man. And what you're doing is you're taking a snapshot at that moment of those hormones. Now, next season comes, I'm a tomato farmer, I got my tomatoes out, just so happens that I saved seed for my tomatoes, should, and then I now have the same, literally, not the same genetics, but similar genetics for my plants for the next generation. And right before I start seeing this stretching and elongation, I do a little bit of a foliar spray with dilution with water with these fermented plant juices. And what happens? They absorb those cytokinin, gibberellic acid, and auxin through their stomata and then treat it as if they produced it themselves, just like when humans synthetically make auxin and spray it on the plant. It has the same effect. So now the plant doesn't have to work as hard to produce these hormones. It can work on its root base, maybe nutritional uptake, and it just doesn't have to spend that ATP and those calories and that energy producing those hormones. That's the theory behind it. Nobody knows if it works. But fermented plant juices, yeah, so it can be plant phase specific, or you could do a general one, which we'll look at in the movie, where I basically just take a bunch of fast-growing weeds. Fast-growing weeds have a lot of auxin in them. They're going to have a lot of growth hormones. Chop them up, ferment them, and then put that onto a plant that I want to have grow quickly. Now, when a plant takes up a gibberellic acid molecule from itself, or from a synthetic source, or from another plant, it doesn't know the difference. It's still the same molecule, right? Just like the difference between organic and conventional, a plant doesn't know the difference between the nitrogen. It doesn't. It's a molecule. It's down to the molecular phase. It can't tell the difference. So it's the same kind of thing. That make my point okay? Do I need to keep rambling about that? Okay. Yeah, so there are, like I said, known plants, like mugwort specifically, has an incredible amount of auxin. So there's natural farmers that grow mugwort just to use as a fermented plant juice. Okay? It doesn't take any fertilizer to grow. Put it out in the soil, it just grows like a weed. It's a wort, it grows like a weed. So they harvest it up, and then use that gibberellic acid or that auxin, and they spray it on the plants. Okay? Fermented plant juice. Nobody knows if it works. People swear by it. Why do we use it? I already mentioned this. I should really look ahead of my slides. Exchangeable plant hormones. Or is it better that I mention it and then there's the bullets to reiterate? I don't know. Exchangeable plant hormones. Right? And then also the bacteria, fungi, protozoa that are on the outside of the plants, definitely, and maybe the microorganisms that are on the inside of the plants. The theory is there with the endophytic organisms, the mycologists are telling me, based upon their definition, endophytic, they literally can't exist outside of the structure of the plant. Now, what is it in the structure of the plant that keeps it alive? Is that available in the solution? We don't know. It's very simple testing to come up with the answers for these things. It just takes somebody to ask the questions and to be able to ask people for the money to come up with the answers. Okay? Exchangeable plant nutrients, of course. If you forget everything else, guaranteed, I'm taking nitrogen, phosphorus, potassium out of that material, and I'm making a plant available form and putting it right back into another plant. Yes, we know this happens. Plenty of farmers take their grass clippings, soak it in water overnight, and then spray that solution all over their land. You do that, right? Okay, because you're supposed to. What are you doing there? You're taking all the phosphorus out of those grass clippings and then putting it back into your environment. It's all it takes. Take your grass clippings, put it in a 55-gallon barrel, and soak them overnight. Strain it up. Take your water, put it right back into your grass, and you have just taken all the phosphorus, put it right back in there, and you've closed your system. Okay? So, we know for a fact that this happens. So if nothing else, it's what? Plant food. That's why I call it plant food. I don't call it anything else. I might call it a microbial inoculant, but essentially, to me, it's plant food. It could be a whole lot more.
Question.
Yo!
How long can you keep that fermented FFG?
That's another question. Good question. We don't know the answer to, but people are holding on to it for a year or 2 or 3 or 4. Essentially, if you're not thinking about the microorganisms and you're just thinking about the oxime and the nutrition, it could stay good forever because it's still in a water-soluble form and there's no volatilization because you close it in a jar. Now, if you include microorganisms into that, those microorganisms in the jar certainly could break down those hormones for nutritional need because there's nothing else to eat. Now, the fact that half of it is made of glucose, sugar, indicates to me that there's plenty of food for everybody and that they might just exist doing their own thing. You understand what I'm saying? So, as you'll see in the film, if we get to it, the number one material that all microorganisms will go for first is glucose. So as long as there's a steady availability of glucose in the environment, microorganisms will always have a food source. Okay? IMO4, guys. I call it a super compost or a compost on steroids. Because, as I mentioned earlier, all composts have indigenous microorganisms in there. The question is, am I putting more in there for a goal? I'm trying to expedite decomposition and the spread of the microorganisms through the material. It's a soil amendment, a granular soil amendment. I was going to bring you some, but I didn't. We're going to hold that for the next class. Or it can be used to make a tea. So you can put it in like an onion bag and let it bubble out with some water, just like you would make a vermicompost tea or a compost tea. Plant-based material, which is inoculated with indigenous microorganisms. That's what it is. Generally, it's a carbohydrate source that has been inoculated with indigenous microorganisms. Now here comes the question. Everybody always asks me, what should I use as my carbohydrate source? I leave that up to you. There's plenty of people doing experimentation, like myself. I used to preach one thing and now I don't, because I found something that works better. And then I started preaching another thing, and now I stopped preaching any of them because I'm almost back to the, okay, yeah, mill run works so damn well that, I'm back to mill run again. I don't know. It's just, it's tough. I was using sugarcane bagasse, coffee parchment, albizia, what do you call it? Wood. What's the word?
Clippings?
Sawdust. And then, yeah, there's so many others that look straw, looks like a possibility. So I'm experimenting with them. I can honestly say, I'm going to back the Cho Globals on this one. Nothing right now works better than mill run. It's true. But like I said, if it works half as good and it costs you nothing, why not use twice as much, right? No, it doesn't work that way. But, so, plant-based material with indigenous microorganisms, usually a carbohydrate source, okay? Thermophilic. Thermophilic is what happens when your compost gets hot. And what's happening there is microorganisms are moving around at such a rate and replicating at such a rate that it builds heat. Friction is what causes the heat in thermophilic decomposition. So many microorganisms moving around at such a rate that heat starts to build up. Okay? So IMO4 certainly has a thermophilic property to it. Throughout the process, in 2 points of the process, we get the temperatures of this material up to 120, 130 degrees. Why? We're killing off pathogens, we hope. Who knows? There's rapid microbial reproduction going on in IMO4. Maybe not when IMO4 is finished because it's stable at that point, but throughout the process of producing IMO4, there is a rapid microbial reproduction. I can stress that in the fact that I take a handful of microorganisms and turn them into a 300, 600, 900 pound pile of microorganisms. Okay? Many steps are involved in the IMO4 process. In fact, it's about an hour of the 2-hour film. Takes a lot of steps, but each one has its purpose, certainly. And in conjunction, it's meant to be used in conjunction with mulching. Why? Because IMO4 is called indigenous microorganism 4. It's not called indigenous microorganisms 4 with an umbrella. Indigenous microorganisms don't do well in the sun and the rain. They belong in the soil, away from the sun and the rain. So if you can simulate that type of environment for your IMO4 by using mulching and covering your indigenous microorganisms, you'll be better off. This will all make sense if you don't know what the heck I'm talking about once we get to the production. In so many steps, breaking it down, I typically will use, I keep saying the same word. I use breadfruit to start off my IMO4, shave it, dry it, steam it, put it in a hollow basket. I take indigenous microorganisms from the environment and place it on top of my basket, let them inoculate my breadfruit, and it starts to look like this. Full of mycelia, look at all those mycelia. Tons of mycelia and all different kinds of colored bacteria. Mixing it with sugar so that I create anaerobic conditions and fermentation. Mixing eventually it with water and then the carbohydrate source, letting it sit and ferment, causing my carbohydrate source to become heavily inoculated in the indigenous microorganisms. I then mix it with field soil and then let it sit, ferment, and then I'm left with this wonderful granular material which is called IMO4. I know that was quick because we need to go through the process. Like I said, it takes a long time. Why do we use IMO4? Well, our main goal of using IMO4 is to increase soil biodiversity. Did we learn what the importance of biodiversity is today? At some point? Yeah, we did. Okay, so increase soil biodiversity, where it helps replicate forest floor dynamics, rapid decomposition, retranslocation, organic material, the whole list of the forest floor almost you can substitute for IMO4. Inorganic matter. And this material allows non-plant available nutrients to become plant available through mineralization. What I'm doing is adding biodiversity so that as organic material enters my environment, you have rapid decomposition and nutrient availability to plants. Also, I don't really care what my organic material is because I have so much biodiversity in the soil that guaranteed there's going to be a microorganism that can break down whatever I put in there. So whatever I have available is what I use, right? IMO4 finished product. I hope to have some for you guys for next week. I have some IMO. I have to make IMO 4 today after I leave this class, so I should have some ready. I have to go make 7 piles of it after this class until about 8 p.m. If you can tell, this material, there's a surfboard, yeah, it's a longboard. There's a 10-foot ladder. So that's quite a bit of material. I don't know if you can tell by scale. To move around, total weight with the soil, about 900 pounds. Making 7 of those in a day. Sometimes I make 12 of them in a day. My chiropractor absolutely loves me. So I tend to bring young, excited individuals out to the field with me so they can learn about natural farming. Help me spread my piles, right?
So your flooring is cement or is that dirt floor?
All IMO is made on a soil surface, okay? Never, ever, ever on cement. Why? Because microorganisms need a place to escape or find their equilibrium. So one of the microorganisms that lands in the middle might be like, wow, this is way too hot, there's way too much water, I want the dry, crispy edge. I want the brownie corner, right? Lands over here. Sends up a spore, lands where it wants to go, find a nice little niche. Ooh, this is cozy, this is where I'm going to be. Some of those might actually be on the soil surface, touching the soil surface. If you have cement, as soon as those spores hit the cement, they die. There's no organic material, there's nothing. At least the spores can at least hit the soil, and it can re-spore over back into your pile if you want it to. Okay. Well, IMO 4, of course, improves soil dynamics I'm adding soil biodiversity. The whole 3 slides in the beginning about biodiversity, I'm doing all of those things when I'm adding IMO 4. I'm preventing erosion of my topsoil if I inoculate with IMO 4. Remember the graphic of the hyphae all around the soil surface of 1 millimeter of soil? Essentially what I'm doing is adding biodiversity so that I can help retain my topsoil. It is also used as a pen inoculant for livestock. It is a major ingredient of the deep litter pig system and the chicken system. Okay? When we do the deep litter system, we keep our indigenous microorganisms, our IMO 4, up near the top where the pigs exist so that they can do their forest floor functions right up there with the pigs. The pigs can eat it. They can, the IMO 4 can quickly break down those high nitrogen feces and urine and all those things. So it's a very, very important part of the IMO, or the deep litter piggery system. In addition to the chickens, we're going to use a special chicken coop that leaves area for IMO on the floor and causes no flies, no stink, guaranteed. This, as far as agriculture, or as far as livestock goes, this system is going to revolutionize everything. As far as the whole agriculture side goes, like I'm about ready to just jump over with Mike on the livestock side because he's getting these looks from universities all over the country that are just like, wow, you guys have done something here that could seriously change the face of agriculture. And it's almost like I want to jump on that wagon with him, but I'm so into my ag side, but it's kind of a conjunction together.
Take the plunge.
Man, I do. I just don't know, I don't know anything about livestock as far as like themselves. I know about the system, but like if you wanted me to raise a pig, that would probably go sour pretty quickly. I do well with dogs. They understand English. Also, as a feed inoculant, IMO 4 inoculating my pig feed. Why not? You're just taking the natural things that it would eat in the environment, fungi from the forest floor, bacteria, placing it on their food, and they consume it. You know there's no pathogens in there, right? Nothing that'll make anybody sick, mainly because you put it through all these rigorous, this gauntlet of conditions, right? Also, there's no pigs in the involvement of processing the food, so there's very little chance of viruses or infections being passed around. Okay? Alright. And then of course we have our fermented animal materials. We have fermented fish waste. Some call it fish emulsion, some call it FFJ, whatever they call it in their damn acronyms. Lactic acid bacteria solution, this is what you're looking at right here. This is what I take on a daily basis, give to my dogs, and I would give to all of my livestock. Water-soluble calcium, which calcium being a macronutrient and a pH stabilizer, super important. All farmers need to have a calcium source for their plants. It's one of those nutrients that are lacking in the environment. It's very plentiful in the environment, but not plant available in the environment. And then of course, something called IMO5, which I strongly advocate. We'll talk about that. Fermented fish waste. Oh, Bob loves when I make fermented fish waste. Essentially, it's a stable nitrogen, calcium, and magnesium and iron among many other nutrient fertilizer. Stable, meaning water soluble, and it can exist in that phase in storage. Very stable. It's made from fish innards, skin, flesh, and bones. We use osmotic pressure, just like the fermented plant juices, to extract the nutrients from the cell walls. The cell wall being the semi-permeable layer. Who cares if it's a plant or an animal? It's still a semi-permeable layer. Indigenous microorganisms break down the material. So the fact that I'm exposing the processing to the environment, I'm incorporating a lot of indigenous microorganisms into the processing because it's a very high nitrogen or macronutrient source. So if I put a bucket of this stuff out, microorganisms are going to find it. They're going to land there and they're going to be happy and they're going to start reproducing as quickly as possible. So in addition to the nitrogen and all the other wonderful nutrients that are in there, this is also a great way to inoculate the outside of your plants with many different kinds of microorganisms. Okay?
Do you use same 1-to-1 ratio?
No, it's a little bit, it's more of a layering.
There.
Yeah. So for example, take a fish head and guts, some fins, cover it with sugar to the point I don't see any more fish. Add another layer of fish, add another layer of sugar so I can't see any more fish. And then it would usually fill up a 5-gallon bucket doing 2 layers. You'll see in the film. And after a certain period of time, it could be 7 to 10 days, you're going to have some extraction of those materials, very high in water, very high in nitrogen, calcium. And then you can extract that out. Now, the materials that are still left over, there's still plenty of bones and skin that aren't broken down after about a week. Add a little bit more sugar, let it sit for a couple months, and you're going to have a different fermented fish emulsion. It's going to be a different chemical makeup because it's accessing different sources of nutrients in the bucket. So, and then after that one, you harvest that one, you got a little bit left over, you can always do something with something and something. And as you go down, I'll explain to you when we talk about the calcium that nothing goes to waste. Okay. Why do you use fermented fish? Well, it has a high nitrogen, phosphorus, potassium, NPK, generally right around 511. It's really just a guess based upon what our comparison to fish emulsion that we buy at the store. It's a very similar growth. Now, there's a chance it might be like 1.1.1, and the microorganisms are causing that growth, expansion and growth, and just the little bit of nitrogen that is there. We don't know. We haven't done enough analysis on it. So. We know it has high nitrogen because it comes from fish, but those numbers could be way off. Right? But typical fish emulsion that you buy at the store is about 511, and based upon the rate of growth, we expect it to be very similar. Wouldn't it be great if it was like 911? It'd be like, yeah, it'd be like literally the highest nitrogen rating of any organic amendment you can get. Leave me alone. I'm busy. It is also water soluble. So the nitrogen that's in there, it's because it's stable nitrate as opposed to ammonia or nitrite. Nitrate very stable and the most plant uptakeable form of nitrogen. Literally, you spray this on the outside of the plant, on the roots and in the soil, it's going to absorb every bit of it. Forget about the nitrogens, calcium, magnesium, plenty of nutrients in there. Foliar and soil amendment, it also has amazing effect of deterring pests. Why? It stinks. I actually have some of this that I mix with tobacco in a solution, and I spray it on my plants, and boy does that work. The insects don't go anywhere near my plants for 6 days. I think that it's because of the absorption of the nitrogen. They absorb some of that tobacco and nicotine into the stomata, and it sits around the stomata for a couple days. It might confuse the plant. The plant might get high, who knows?
You started to grow tobacco.
Yeah, I mean,
To experiment with it.
yeah, not cigarette tobacco, that stuff's gross, but yeah, if you can just grow regular leaf tobacco.
Now, do you cover them?
No, you want to have gas exchange, but you want to put like a permeable layer, like a t-shirt or something, so you have gas exchange, but you don't want flies.
Or you just open the plug and drain out whatever?
Or you strain it, just dump it out and strain it. You'll see in the film. Lactic acid bacteria solution. It's a form of cultured lactic acid bacteria. Lactic acid bacteria is the end result of fermentation. Okay? When organic material is fermented, the last organism to be standing is lactic acid bacteria. It's also one of the main probiotic bacteria in your gut. It is one of the super microorganisms, like the supermen out there. These things are amazing. Used as a foliar spray in agriculture already as a antifungal. This microorganism uses hyperparasitism. So what it does is it lands on whatever surface, finds a nutrient source, and exploits it. Most times than not, another microorganism caused the nutrient source to be exposed. That microorganism is out of luck. Sorry. Because they come in such droves and such numbers, and they have such a size for them as compared to a lot of other bacteria. Essentially, lactic acid bacteria solution is whey from when you make curds and whey. Little Miss Tuffet, right? What are curds and whey? Well, curds are cottage cheese, and whey is lactic acid bacteria solution, which is what's left over. It smells like rotten milk. You'll see next week. It stinks. Like I said, it's the end product of carbohydrate fermentation. Well, I need to start off with a source for my lactic acid bacteria. One of the best places to acquire lactic acid bacteria is on the outside hulls of white rice. So I make a rice wash water, let it sit and ferment on its own for about a week. I add a little bit of milk, let it sit for another week. Curds and whey are created, and I take out my whey, add a little sugar so I can put it on the shelf, and we're ready to rock. It's a very simple process. Why use it? Well, lactic acid bacteria being the key factor in fermentation means it's super hardy. That means while everybody else is getting their turn at the material, the lactic acid bacteria is just sitting in the back going, I'm going to wait my turn, I'm going to wait my turn, I'm going to wait for this to happen, I'm going to wait for you to go, all right, you go ahead, eat that stuff, I'm going to wait. And that means that microorganism can withstand these crazy changes that might come when these microorganisms start breaking down this material. They can sit back and wait. Temperature, pH changes, whatever, they're cool. Eventually, there's not enough nutrients for everybody else, and everybody takes off because they've just made this horrible environment for microorganisms. That's when the lactic acid bacteria comes in and goes, I'm going to finish this off, and I'm going to sit here and wait for more materials to show up. Okay? So they're hardy. They are the tough guys in the microbial world. It acidifies things, so that's why lactic acid bacteria is used and is the main ingredient of inoculation for kimchi or sauerkraut. Okay? Because it acidifies, it creates an environment that is really good for itself and not too many other microorganisms can exist. Which is why kimchi could sit on the shelf for a very, very long time. Digestive health of livestock, of course, it's probiotic. Livestock pen maintenance. Remember I said it's hyperparasitism? So if I take lactic acid bacteria and I spray it on the side of my pig, right? My pig just was in a cement pen, not like a natural farming pen, but a typical USDA approved pen. Right? And it lays down in its poop, and it's got just bacteria blacks. Everybody's pig's got these black spots, they stink awful. If I take lactic acid bacteria, walk up to my pig, I spray it on the side of that pig, I come back about an hour later, what does that pig look like? Looks clean, and he doesn't stink. Why? Hyperparasitism. There was a microorganism that was consuming the poop on the side of the pig. It was releasing sulfur, methane, stinky, stinky stuffs, right? So lactic acid bacteria comes along, boots everybody out of the way. I'm bigger, tougher than you, and I want your nutrient source. And within a couple minutes, those microorganisms don't have a nutrient source. They cannot make that stink and that smell. They die. The lactic acid bacteria consume them because they're a nitrogen or they're a nutrient source. And eventually the only thing left over is lactic acid bacteria. So when I spray this on the feed, on the face of my pig, and all over the pen, and the pigs love it. They're like a little bath, And they know that they don't itch, and the flies don't bite them after you spray them, and all these wonderful things happen. So it is one of the main ingredients of the natural farming livestock routine. Okay? It's antimicrobial. Like I said, it robs the nutrient source from other microorganisms. It also deters pests. Why? It stinks. It smells like rotten milk. Spray it on the outside of your plants, not only are you getting rid of the fungi and bacterial infections, but you're deterring aphids and wonderful cabbage butterflies and all these things. Okay, gotta be careful when you use lactic acid bacteria because it will consume any nutrient. So you're not gonna spray fish amino acid on the outside of your plants and then come over 20 minutes later and spray this stuff on, because whatever you just sprayed on your plant, the lactic acid bacteria is going to consume that. So it has to be used at specific times, at some specific rates, and for specific reasons. You got to watch it. Start spraying that all around your. I know people that are like, I got some great lactic acid bacteria, and I sprayed it all over the roots of my coffee plant. Wow, that's great. Now you have no nitrogen left and absolutely no sulfur and all these wonderful things that you need. You need to put that stuff back in now. They don't understand how to use it. Okay. Water-soluble calcium. What better place to get calcium from a agriculture byproduct of which we have tons and tons of? Bones. What we do is we'll take pig bones, cow bones, usually a large mammal bone. We char it, which means we bring it up to heat so that the outside becomes ashy and you can tell that the inside becomes charcoal. We then mix that material with white vinegar, which we make ourselves, which is very easy to make and affordable to make when you start making it yourself. You mix the two together and you let it sit for a very long period of time, 6 to 8 months. I have some going that I believe didn't go so well because the vinegar evaporated on me because I didn't cover it correctly. But I'll try to bring it next week and maybe we'll just reuse it to make another batch. So essentially what happens is vinegar is acetic acid. Okay? Acetic acid, it breaks down the carbon bonds through chemical reaction releasing nutrients from the bones. Essentially, it's the acid is releasing the calcium from the carbon. What does that mean? It means the calcium is taken out of the bones and brought into the vinegar, which makes it water soluble. So what you're doing is extracting magnesium, calcium, and making that available as an amendment, a liquid amendment. So it takes several months to extract it out. What happens when you take a chicken bone and put it in vinegar and you let it sit for a week? Remember that in school? What happens? It turns all rubbery, right? Remember that? Chicken bone goes in and you take it out and you go bend it all over the place. Why? Because the vinegar took out all the calcium. You're only left with carbon and the tendony material that the bone is made out of. Why is the bone hard? Because of calcium. Vinegar removes calcium from bones. Take it out, you have it water soluble available. You can use it as a plant foliar amendment. You can use it as a soil amendment to raise your pH. You can use it to add calcium. I actually don't talk about that one in the film. So raised pH, it has high levels of potassium, magnesium, phosphorus, and other micronutrients. It has some nitrogen as well. And of course we got IMO 5. What is IMO 5? Well, IMO 4 was plant-based amendment, right? But IMO 5 is going to take that plant-based amendment and we're adding some animal-based amendments, mainly nitrogen in the form of fish amino acid or the fish juice. Why are we adding that? What are we trying to even out? The carbon to nitrogen ratio. IMO 4 is extremely high in carbon. The microorganisms in the IMO 4, chances are, have consumed all of the nitrogen in there. What better way to activate this material than to give it a nutrient source, nitrogen nutrient source, before you put it out into the field? Here's a better proposition. In addition to adding nutrient source, why not give those microorganisms a stable home in the form of biochar? Biochar is going to be wood that is cooked at a very low temperature with very low oxygen, creating a charcoal, almost like glass, like you hear it. It's like charcoal you buy, the Kiabi charcoal you buy at the store. This is what we're talking about. This is going to be biochar. Black material. It's not white. It's a very, very black material. And what is left over in biochar is essentially just carbon. But biochar pieces have an extremely high what?
Openings.
Surface area.
That's it.
So, if you were to take a particle of biochar and stretch it out so that all surfaces, kind of like a map, right? So you take a ball and it's a globe, right? If you made like a map of that little globe and stretch it out, but you pull out all the wrinkles and all the ridges and all the concaved areas, the area on which the surface area would compared to the dimension of the ball can be 1,000 times bigger. Just like with clays, I've given the analogy that if I took a clay, it's very similar in its surface area. If I take a particle of clay, which is less than 2 nanometers across, say I blow that up to the size of a football field, so imagine this giant big ball of clay, and if I stretch that out with all of its surface area, the 100 yards of the ball would actually stretch out to an area the size of the United States of America. That's how much surface area we're talking there. And what the surface area gives is a place for microorganisms to camp out and do their processes, place for them to wait for nutrients to come in. The biochar itself is a nutrient source for microorganisms. Essentially, it's a condominium. No, it's an entire city per ball for microorganisms. So why wouldn't I take this material that is high in microorganisms and high in carbon and add a little bit of nutrient source to aid in decomposition and then give those microorganisms a stable place to stay? That's what IMO 5 is. IMO 4 makes a little bit of biochar and a nutrient source. It makes more sense to me as an agriculturist to inoculate your field with this. Okay? That's IMO 5. IMO 5. Incredibly biologically rich mulch. That mulch is about 8 or 9 feet long and about 5 feet wide. That is enough material to inoculate about 5 acres. You barely dust the surface with the material when you apply. We learned about that on application day in the film. Okay? Well, we use it, like I said, to have an even carbon to nitrogen ratio, more surface area, and a nitrogen source for the microorganisms. That's it for the lecture. We can watch the film. I want to talk about the next classes real quick. Material production and application. This is a hands-on. It's really the best way to learn natural farming. It's next week. Rain or shine, folks. Bring rain gear. Bring boots. Bring gloves. Bring mosquito repellent. I don't want to hear any complaining. Just joking. Come ready to mix and to get dirty. Okay? It's a really, really good time. We do it in the agriculture area in the back under the tents. So if it is raining, we'll still conduct class in a rain-free environment. Right? Then we'll talk about our natural chicken production. Like I said, Michael DuPont's going to do that on the 3rd, and then I'll be doing the swine production day. A little bit of a field trip involved in that. If you have like a van, and because we're going to be carpooling, would probably be the most efficient way to do things. If you have a van, maybe bring it. We can put everybody in a van and be sustainable as possible. Okay. Also, Gino's in my other series of classes. If you're interested in learning about more of this stuff, I get into the science and the understanding of these practices. And I talk about plant morphology and physiology on Monday. I'm going to talk about plant nutrition. This is kind of a continuation of other classes that we've had, but you're really more than welcome to come in and pick up where we left off. I do film the classes. All but one got filmed. One of them didn't get filmed last week. So you can play catch up if you wanted to. I tend to do a little bit of a review at the beginning, but either way, you'll really understand how plants take up nutrients and that it's more involved than understanding nitrogen, phosphorus, potassium. I mean, it's so much deeper than that. So I usually talk about 2 to 4 hours on these classes. Introduction to microorganisms. I'm going to do a little bit of repeat of some of the stuff we talked about today. Maybe it's best to reiterate it and hear it again, but there'll still be a couple hours of new material there. Soil microorganisms, we're going to mainly talk about decomposition for like 2 hours and understand how soil microbes decompose, what nutrients are then available, and it's a little bit of the chemistry behind it. Don't mean to scare you. Plant-associated microorganisms, we're going to be talking about endophytic and exophytic microorganisms on that day. And then we talk about an introduction to entomology and nematology for the 21st, where we're going to learn how to identify your pest insects, how to come up with approaches for treatment, understanding biological techniques and what a nematode is, and that most of them are actually very good for your plants, and yada yada. Okay? These will be kind of shorter. They're not all going to be about 4 hours. I don't think I could talk for 4 hours in soil microorganisms, but we'll certainly introduce you to some of the major players and the decomposers. And I kind of highly doubt that, I don't know if you guys are going to sign up for those, but those are pretty specific, and I doubt if I get 6 people for those, but I'd be happy if we did.
Which one?
Any of the later ones. Like the microorganisms, I think.
Yeah, paying foolery. You gotta have.
Oh, I'll have them, but like I said, if there isn't 6 per class, All right. Take a quick break, and I'll pop the movie in, and you can watch it if you want, or you can take off. Don't really care. But yeah, I'll do that for you guys. You can watch the film. It really goes through a lot of the stuff we just talked about, and step-by-step instructions on how to make the amendments and such.
What time of day are your classes?
Those are 5 to 9 p.m. on Wednesday. Okay, do about 5 minutes. I'll come back and hit play.
plant nutrition, that's interesting.
So you send up for
The
when?
The part of the series you sent up for, these little.
Yeah, it's 9 parts. Yeah. Well, it's about $40 each session. So, honey, you guys gonna come next week? Say yes. See nothing about eyeball rolling.
Saturday.
Huh?
I said, I want to come on Saturday, but marijuana, because the parade and all that.
Yeah, but do your thing. You know, every year, it's that guys, we do the kind of smoking tent, you know, have you ever seen that? Pass out smoking. You never did smoking that year? Every year they pass out smoking. You know, see the trailer and stuff like that. Yeah. They pass out smoking to the parade watchers and stuff like that. So I think they're gonna do them again this year. Are you guys gonna do it?
What time is Monday's class?
Oh, Monday's one is 5 o'clock.
Afternoon.
Yeah. 5 to 9.
I usually don't look at me because I usually work sometimes till 6.
5 to 9. And then that's a makeup because we didn't have a class on this past one. So we're gonna have on Monday and then Wednesday again.
Yeah, this Monday's a makeup. I was out of town. They were kind enough to let me reschedule it.
I gotta call some of my friends. I gotta guarantee that this event's not gonna happen this coming week.
I would heavily worry about the class next week on Saturday. See if you can get a few more.
Up to you. Grandma's not going to remember it. You know, take her to the Chinese forward.
Your mom. Oh yeah, your mom, yeah.
Yeah, she needs to watch the bird.
Yeah, leave it right there in front of Starbucks. Yeah, one chair. And just stay. Okay, Ma, coming
I
back.
come back.
Where you are? This food not already. And I bet you're still 30.
Is that not enough so you can get up? You have to call them tomorrow. Today.
What you do is get $10, no, $20 worth of Starbucks coffee and stuff like that. Now, you know, as soon as she run out, you guys make sure you keep on filling them out there.
I'll come back. I promise.
You know, it'd be funny. Parade power and everything like she's still sitting out there sipping her coffee. 5 o'clock in the afternoon. You know, Korean restaurants and stuff like that, wondering what the heck you were supposed to do.
So you got some of this stuff on YouTube?
I put all my classes up on YouTube. If you guys want to write down my channel, it's Agriculture Education Center. So I have all my business plan development stuff and
Is it .com or .edu?
no, it's YouTube. It's on YouTube. So you gotta go to YouTube and search the channel, Agriculture Education Center. Oh crap, I forgot I still haven't changed the titles of the other class. I'm on it. Apparently I'm kind of busy. Why isn't this working? You silly machine. Okay. I don't like PCs, I never touch them. They just aggravate me to death. Like I gotta use a DVD. Everybody,
How long is that video?
don't ask it long.
We can stay for a period.
Oh, yeah, after the jam time.
Oh, yeah.
No. I should get cream cheese in there. But I still make the jam. Unless I go early tomorrow.
As if I have an actual copy of it. So yeah, it's a long movie of me reading off a cue card. No, just the beginning and the end. I wing it in the middle.
So it's fiction then?
Yes. Damn it. So I have a bunch of copies because the guy who helped me draft this film gave me like 3 copies before I said it was okay. There's like editing errors and all. I hope I have a finished copy.
James, I gotta go. I got my mom's retirement party I gotta go to.
Go crazy, man.
Alright,
Don't hurt yourself.
here's the stuff there.
I think this is an actual copy. Okay. It might be an edited copy. We'll see. Either way, here it is. You guys are the first ones to see this. I'm James Rushing, and I'm going to spend some time today talking with you about natural farming. Natural farming is a style of farming which brings together techniques used by farmers from all over the world for millennia, all of which use naturally available materials and improve crop production, increase farms' overall biological diversity, and eliminate the need for costly plant and soil amendments. Throughout the centuries, societies have developed amazing natural agricultural techniques that utilize plant-based materials, animal byproducts, and indigenous microorganisms like fungi and bacteria. But only now have we been able to bring all of these techniques together so that farmers can incorporate this totally sustainable natural farming system into their modern agricultural practices. Natural farming is not just an agricultural use of naturally available materials. It is a complete lifestyle choice that farmers make to help improve their land, their health, and the health of their customers and neighbors by using only plant and animal-based amendments and refusing to use manufactured chemicals, commercial fertilizers, and any other material that is not locally available and sustainable. Natural farming goes far beyond modern organic farming in that only materials and amendments made on the farm are used on the farm. This is done through the gathering and reproduction of specific plants and microorganisms and utilizing these microbes and plant matter to improve crop and soil health. It is a new field of study which focuses on plant and soil health from a microbiological standpoint, an agricultural approach which has not been looked at closely by the scientific community until today. Today, growers from backyard gardeners to large-scale farmers use natural farming techniques. Typically, the growers who use these techniques are looking to eliminate the need for purchased amendments for economic reasons. Use only naturally available sustainable materials for environmental reasons, and believe in alternative agricultural approaches for sociological reasons. These growers see a value in incorporating biology into their farm system, stimulating a biologically balanced system, as opposed to conventional techniques which aim to eliminate biology and result in unbalanced or disrupted biological structure. There has been a change in attitudes towards conventional farming in recent years, and I believe the adaptation and utilization of these practices by farmers in all socioeconomic settings could improve countless environmental, economic, and public health issues. Recently, scientists have begun studying these natural farming techniques. This is important because there is a lot of science behind the use of these farming practices, much of which is covered under 4 specific fields of study. Microbiology, the study of microscopic organisms. Soil science, the study of chemistry and the dynamics of soil. Horticulture, which is the study of plants and crop production. And finally, plant pathology, the study of relationships between plants and pathogens. Scientists who study these fields help farmers develop the best techniques, and more importantly, help explain why natural farming has been able to show an increase in crop production while reducing costs and inputs. Let's talk to some of these scientists about their fields of study and how natural farming has such a positive effect on crop production. And then we will discuss several natural farming materials typically used by practicing farmers.
Hi, my name is Brian Perry. I am an assistant professor at the University University of Hawaii Hilo in the biology department. For me, in its most simplest form, biology is just the study of all living organisms on the planet.
My name is Jonathan Malaya. I am a molecular microbiologist at the University of Hawaii at Hilo. The bacteria is what I'm most interested in. Really, I'm looking at how the bacteria interact with different hosts. Now, these hosts range from potentially insects, potentially plants, as well as other microorganisms interacting with each other. Just for the idea is that microbiology is a lot, encompassing a lot of material. People think that microbiology is just a study of small little guys that don't do a whole lot of things. It turns out they do a lot of interesting components associated with it. So you have archaea, you have bacteria, you have the viruses that are oftentimes put into this category as well, and the fungus are part of it. But to study all of it is kind of a unique idea nowadays. People are now looking at community structures rather than just looking at the individual pure cultures, which is the classical microbiology type of thing to do. So when you think about biology and microbiology, for me as a microbiologist, we really have to look at community dynamics nowadays rather than just pulling out the individual microorganism and saying, how are they really doing it in that type of actual environment? So in the past, microbiology really was focusing on pure cultures. The only way to study these microorganisms was to pull them out of their environment, isolate one type of colony, and really try to put them into culture so you can study them really well. Nowadays, you really have to do more of the molecular approach, genomics approach. You can study a lot of these guys at a big amount of data by looking at the whole entire genomic sequence of a lot of these bacteria or anything that you might be studying within the actual soil. The interesting thing nowadays is that in the past, these microorganisms, when you study them, you could only really look at the ones that are culturable. So when you talk about these pure culture organisms, you gotta think about it in the form of, well, these are the guys that you can grow in a laboratory. Turns out we're not able to grow, like the majority of them, over 99% I think of the actual microorganisms are unculturable, which means these guys are playing a large role within the environment, within the actual community structure of these soils, or any environment that you might be studying. So with the new field of genomics and doing more molecular approaches, you can study a lot of these different types of actual microorganisms now and see how they're actually playing a big role rather than the ones that you can just grow in culture.
Name is Norman Aaron Kahn, a professor of horticulture at University of Hawaii, Hilo. Beneficial microorganisms in the soil is just one of the categories of the many, many organisms that you can find in the soil. They're mostly called beneficial because they benefit plants. They also benefit soil in general. And they benefit in plants, the way they benefit plants is they make plants healthier. And we talk about healthy plants, those are plants that actually grow in their potential, the fullest potential. And also they're able to resist pests and diseases and plant pathogens as well. So they're beneficial because they suppress microorganisms, pathogenic microorganisms, and they also are involved in the mineralization of a lot of essential elements that plants would need.
My name is Michael Shintaku, and I'm a faculty here at UH Hilo. I teach plant pathology, genetics, and microbiology. Plant pathology is the study of plant diseases. There's a lot of things that can cause plant disease, but mostly what I study are the things that are the biological causes of plant disease: bacteria, fungi, viruses, nematodes, things like that. So plant pathologist would be somebody like me who studies that kind of stuff, and in my case, for the most part, I teach plant pathology. A plant pathogenic microorganism is an organism causes disease on a plant.
Mm-hmm.
First of all, a plant disease is some condition where the plant is not performing to its genetic potential. It's kind of the definition that we use. So plants can, they grow depending on their environment to some extent. And if they're not, if things are not right, it could be nutrition, it could be light, it could be water, all these things can cause disease. But the microorganisms also can cause disease. So it can be environmental, plus it can be also a pathogen. So the microorganisms that cause plant disease, they're plant pathogens.
Truthfully, the world has been farmed by natural farming practices for over 10,000 years. From the first farmers in Mesopotamia who utilized their composted food waste, to the Amazonian Indians who created the terra preta technique that used charcoal as a soil amendment, to the American Indians who planted whole fish alongside their corn, to the ancient Japanese and Korean farmers who cultured indigenous microorganisms to produce a biologically rich mulch. We have been incorporating biological systems into our farming systems since the dawn of agriculture. But it wasn't until the last decade that these techniques from all over the world have been consolidated into one methodology or production system. Techniques like IMO soil inoculant, biochar, fish amino acid, and fermented plant juices are finally being used and documented together in the same system. It is only now, through modern information sharing, that we have been able to bring these effective techniques together into one system.
Farmers are not lacking the knowledge of microbiology. I think if anything, they just don't realize what the microorganisms are doing within it. I think they're actually applying and doing a lot of the necessary things to make them do the microorganisms to do the same kind of work that they would know if they studied them. But the manipulations, the changes that might be caused by what they do, they might not realize the significant amounts of changes that might happen within these microenvironments. For example, if you apply too much of some type of actual macronutrient or micronutrient, you actually can hinder the growth of a lot of these microorganisms. They only need a certain amount. So by overdoing it, oftentimes you'll find out you're killing off these microorganisms that are technically beneficial for your crops.
Yeah, this is an edited version. It's supposed to be a question, though.
So as far as the types of microorganisms that are out there, of course, we have, I primarily work on fungi. Many fungi form macroscopic structures, but in reality, the great diversity of fungi on our planet are microscopic. We, of course, have bacteria and the archaeans, the prokaryotes. Then we also have microalgae, and then, of course, viruses. So when most people think of a fungus, they imagine a mushroom. And when we see a mushroom growing out in the woods, what we're seeing is really we're seeing that organism go through sexual reproduction. So a mushroom that's formed by a fungus is simply a structure on which that fungus produces spores, which are the reproductive propagules of that organism. And really the business end of that organism, the large network of cells that it forms, that we refer to as the mycelium, that's usually someplace either underground, exploring the soil, or if it's a mushroom growing off of a log, it might be penetrating throughout that downed log. That's really the business end of that organism. That's where all the interactions with other organisms, whether it be in the soil or associating with a plant or interacting with animal hosts, that's where most of that's taking place. When we look at the diversity of fungi, what we see is that macrofungi, in other words, those that form large macroscopic structures that we can see with our own eyes, those only account for about 10% of all known fungal diversity on the planet so far. So in reality, 90% of the 100,000 species of fungi that we know currently are really microfungi. So these are things that we can oftentimes see, if it's a pathogen or a parasite, we can see the diseases or the symptoms that those fungi cause on their plant or animal hosts. But in reality, most of these fungi are microscopic, and we can't see them without the aid of a microscope or using molecular tools. All right, so on a global scale, we know that there's currently about 100,000 species that have been described, recognized by scientists. But there's lots of estimates out there that predict the diversity of fungi worldwide. These range from about 1.5 million all the way up to slightly over 5 million species on a global scale. These estimates are based on looking at ratios of plants and their associated fungi, insects and associated fungi, and more recently using molecular tools to look at the diversity of fungi in forest soils and then extrapolating this to a global scale. For me, understanding the biodiversity of fungi or any other organism is really, the big question is, why is it so important? Why are we so concerned with biodiversity? Why are we so concerned with preserving it? And to me, it really comes back to really because we understand so little about so much of the life on our planet, especially when we're talking about microorganisms. With estimates of upwards of 5 million species of fungi worldwide, we know only about 100,000 of them so far. And of those 100,000 that we know, for many of them, we have no idea what they're doing in the environment. So for us, trying to understand biodiversity really ties into understanding what these organisms are doing in the environment and what role they may play and how important they really are.
Not really, because no one's really looking at fungi, microorganism, bacteria association with each other. You oftentimes will see it with the higher organisms. So that's why it's really interesting to see how this cultivation of these indigenous microorganisms, because no one's really looked at how they really interact with each other. Okay, so the interesting thing about looking at microorganisms and root systems is that you find out that the biodiversity goes way down the further away you move away from the root system. So what they mean by this is that you can have it over a short period, a short distance, or over a long distance. It depends on how that root system is really going through the soil. But the further away that you go from these root systems, the less diverse that you'll see of microorganisms there. Once you start getting closer into these kind of micro niches that are associated with the roots, root hairs, then you find out a lot of different guys start appearing, and a lot of them start doing some interesting chemistry as well as biochemistry because of that interaction with the plant. So plants are sending off different signals, chemical signals. The microorganisms are now producing different chemical signals. And to see that interaction happen or crosstalk happening between the plant and the microorganism is where the interesting things are to really happen.
If you have an environment, like the rhizoplane is the area around the roots, so phytoplane, the area around the foliage. Yeah. If that is colonized by a more diverse group of organisms, say if there's more biodiversity in that group, that community of organisms would be a little bit more what's the word I'm looking for? Flexible, a little more resilient. Yeah. So if the environment changes, it gets dry all of a sudden, you might lose some of those organisms. Yeah. But others will sort of, do better. So if you have a diverse, diverse community, while the environment might change to be less beneficial for some organisms, it'll be more beneficial for others.
Is there a benefit in adding biodiversity of microorganisms in the soil? Oh, absolutely, and there's a lot of benefits in adding biodiversity in the soil, inoculating microorganisms. In fact, that is I think that is the basis for producing composts and producing vermicompost or indigenous microorganisms putting back in the soil. There is unity and diversity. I always believe in that. If your organisms in the soil is really diverse, even in the presence of a pathogen, the pathogen can only act and can only be virulent and can only attack a plant if their population is left unchecked. And the only way to keep their populations down is to have other microorganisms present around it. They may be present, they may not be pathogenic at all because their defenses are down. So if you inoculate soil with a lot of other microorganisms, that will manage some other population. And if their populations are in a number where they're not able to attack a plant, then that's one of the benefits of having diversity in the soil in terms of microorganisms.
One area that's been real actively studied the last 20 years, but there's still so much to learn about, is how good soil biodiversity is critical in terms of maintaining a healthy soil in terms of minimizing populations of pathogenic organisms. When you start getting out of balance in terms of the conditions to promote favorable organisms, then oftentimes a unique pathogen can come in and run rampant and cause problems for the plants. And there's been quite a few studies that have shown where if you have a soil that's too acid, maybe too low in organic matter, too poorly drained, if you correct the problems, then the pathogen problem may disappear. I mean, and there have been documented cases like with avocado trees where they have extreme phytophthora problems, and the farmer has added compost or organic matter underneath the trees, and it's promoted a change in the soil microflora makeup, and then the phytophthora is no longer a problem. It doesn't seem to, it may be still present, but not present in high enough levels to really adversely affect the tree. So that's one of the things that we're hoping that is funded better in soil science, is looking at how we can maintain optimal populations of beneficial microorganisms so you won't have disease problems. Maybe the organism is still present, but they're never at levels that cause a major problem, and how we can facilitate natural nutrient cycling processes so that the plants won't need so much external inputs and things like that. So that's really going to be key to our future, to be a more sustainable agricultural setting.
So thinking about, microbial diversity in agricultural environments, I think most biologists would simply tell you that, the higher the biodiversity, the better it's going to be, whether or not we're talking about a native forest or an agricultural plot. So we know that these microbes are incredibly important for plant health. We know they're incredibly important for soil health, all these things. So the greater the diversity in any soil, we would assume that that's going to lead to a more healthy system. So when we think about farming methods, doing anything you can to increase the diversity of those soils and to maintain as much of the native microbial diversity there is always going to be very, very important for those systems.
Now that we have an idea about the science behind natural farming, let's learn about several natural farming materials that are used to increase the biological diversity of the beneficial indigenous microorganisms in the environment, as well as improve crop health. First, we will learn how to make fermented plant juices, which can help improve plant hormone efficiency and natural defenses. Next, we will produce lactic acid bacteria solution, which can be used as a natural disease suppressant, integrated pest management tool, livestock probiotic, and as a livestock odor control. Then, we will use fish waste to produce fish amino acid solution, which can be used as a nitrogen fertilizer, integrated pest management tool, and to produce several natural farming amendments. And finally, I will show you how to make IMO4, which is an indigenous microbiological soil inoculant, which is made from fermented, locally available plant-based materials and site-specific indigenous microorganisms. Fermented plant juices, or FPJ, are a simple, cost-effective, hormone-rich plant food. The materials used to make fermented plant juices are actually grown right there on the farm. They're mixed with sugars to create osmotic conditions. They are then fermented and then used to make a beneficial agricultural amendment solution. These materials not only have plant nutrients, but some important plant hormones, including auxin, gibberellic acid, and cytokinin. When diluted, these materials can be used to make IMO4 or be used as a plant foliar spray or soil amendment. Now let's go ahead and learn how to make this simple fermented plant juice. For fermented plant juices, you will need 2 to 4 pounds of green crop materials or weedy materials, 2 to 4 pounds of brown sugar or turbinado evaporated cane juice, 2 5-gallon containers, preferably clay or stone, but can be plastic, paper towels, tissue paper or cloth, a rubber band or wire, a large metal strainer,
a half-gallon glass jar with a lid. And finally, a cool, dry, shady area. Now we're going to make some fermented plant juices. It's a very simple process. We're going to gather some weedy materials from around the agriculture area, bring them back here, and we'll continue that process. Now this is a terrific area to gather some weedy materials to make fermented plant juices. Mainly because it's close to the agriculture area and it has multiple different kinds of weedy materials. Now we're looking to gather materials that include viney materials like this. And these are full of wonderful hormones, and we're going to gather those up like so. Now they grow extremely fast, which shows that they're full of these growth hormones. Just like these broad-leafed weeds. Broad-leafed weeds are going to be dichotic leaves, plants, and they are also high in gibberellic acid and cytokinin, as well as auxin. So we're going to gather that material as well. And the third kind that we definitely want to focus on is going to be the grasses. These grasses are going to be monocot plants, and they grow using stolons along the soil surface, and they grow extremely fast. So we'll gather up some of those as well. Also, on the outside and on the inside of these grasses live microorganisms that we're going to be culturing throughout the process. So we have a nice bucket full. We're going to go over back to the area and see if we can turn this into a water-soluble solution through osmotic pressure. Now that we've gathered some weedy materials from around the agriculture area, we're going to use these materials to make a natural farming solution that is full of gibberellins, cytokinins, auxins, and all kinds of wonderful plant hormones, as well as some microorganisms that live within the plant tissue. We're going to harness those materials from inside the plant materials by using sugar and osmotic pressure. We're going to do that by first weighing the materials that are within the bucket. Scale says that it's 4 pounds. I know that the bucket is 1.5 pounds, so we have 2 pounds of material inside, 2.5 pounds inside the bucket. So I'm going to then do on a 1-to-1 ratio of the materials on the inside of the bucket by weight. I'm going to do sugar. Now I'm using brown sugar. Strongly recommend using brown sugar. Never use white sugar. I also recommend using dark brown versus golden brown, but golden brown does work just fine. Turbinado sugar, which is going to be evaporated cane sugar, is strongly recommended. And this is going to cause osmotic pressure, which will basically leach out and pull out all of the water, the hormones, and all the microorganisms contained within this material. Just like when you make strawberry compote, or you chop up strawberries, mix it with a little bit of sugar, and you put it in your fridge, that material gets pulled out of those strawberries. Same concept here. So let's put a little bit of sugar in here, and we'll weigh this out to just about 4 pounds, meaning 2.5 pounds of sugar. So we have just about the same weight of sugar as we do as material here. And what I'm going to do is mix this sugar with the material. It is recommended you can chop up this material either by hand or with a blender, or you can just leave it as is. What we're doing here is we're looking to get sugar in contact with almost all of the leafy material. Mix it up nicely. sure all that sugar that falls to the bottom gets back on top. And so we have nicely mixed material here. What's going to happen next is the lower pressure of the sugar will pull the water and materials from the higher pressure that is on the inside of the plant materials and the plant cells. Eventually, this will become a soupy material, a very, very thick, viscous material, and it's going to be full of those wonderful hormones and microorganisms. We're going to want to let this bucket sit, but we're going to want to cover it to prevent any insects or pests from going inside. There's two methods you could use here. First, I like to use a burlap bag. It's real simple. Put it up over top of the bucket. Drop it down to the ground, and then it's contained within. The bugs really can't get inside the bucket, and there's plenty of airflow for the aerobic conditions that we're looking for. You can also use the method of stretching an old t-shirt, a paper towel, some tissue wrapping paper, or any permeable layer right over top. You can fasten it with a rubber band or a wire, just like so. So we have plenty of airflow in and out of the bucket, and no pests are going to get inside. We're going to put this in a dark area, away from direct sunlight and cooler temperatures. We're going to allow this to ferment for 7 days. When we're done, it should be ready. We'll come back and check on it then. Well, it's been 7 days since we put our fermented plant juices into this bucket, and we're going to go ahead and remove the permeable layer and take a look at what we got inside. Now what we have here is the fermented plant materials and a syrupy material that is on the bottom. Now that syrupy material is all of the hormones and microorganisms that have been extracted from the materials themselves. We're going to go ahead and just strain those out and put them into a jar. Now the key here is you do not want to squeeze out the materials from the plant materials. Now that's because we don't want to macerate or break up any of the cells that the plant materials still contain. Those cells have not been fully fermented yet. Now we have our fermented plant juices, all finished, ready to be used to make IMO.
How do microorganisms involve in the hormonal changes of plants? Well, first of all, plants produce their own hormones for growth. There are about 5, or now 6 probably, categories of hormones in plants. Most of them are involved in growth, and some of them are involved in flowering, such as ethylene. Some of them are involved in plant stage like senescence, such as abscisic acid. But what we are really interested in are the ones that are involved in growth: auxins, gibberellic acid, and cytokinins. Those are naturally found on plants, healthy plants. But some plants can be helped if you or we actually apply these hormones externally. So since the discovery of auxins in 1930s, we now know its biochemistry and structure of its chemistry. So now we are able to synthesize it. But we don't have to synthesize it if the plants actually can get help from some of our microorganisms. A lot of our microorganisms can produce analogs of, say, gibberellic acid, known genus microorganisms in the genus of, say, Azospirillum or Azotobacter or Some of the rhizobia strains actually have the ability to produce gibberellic acid. And so the more we encourage the beneficial microorganisms living in the soil, the more we encourage its diversity, we can actually produce natural gibberellic acid that will now in turn be produced in the soil and be taken up by plants. And then we know that gibberellic acid in plants, when they're synthesized in plants, they are responsible for cell elongation, cell division, and those are associated with cell growth and plant growth. So the more we have those in plants, we will have plants that are not just growing big, but they can increase potentially their yields. Some plants, again, have the ability to produce their own hormones more than other plants. And so when you when you ferment plant products or plant parts, you're not just extracting the nutrition from it, you're also extracting some of the metabolites, very important, very minute maybe in number or quantity, but they're very important in plant growth, especially hormones. Auxins, for example, are found in the apical apices of plants like the shoots and some of the growing portion of plants. So if you're fermenting that part of the plant, you're actually extracting a very important component in cell division, which is involved in plant growth. So auxins, for example. Auxins, when they are extracted or even synthesized, can actually be applied into another plant and cost just the same as they are produced internally in the plants. So when you're extracting that and you're applying that onto plants, with the help of microorganisms that actually feed on it and also multiply it, they produce some analogs of auxins and cytokinins. They will be transferred to plants and they will be absorbed by plants and they will help in the general health and growth of plants.
Next, I'm going to show you how to use fermented plant juices in field application. Some fermented plant juice formulas are specifically formulated for the phase and development of the crop. Some are very general, like the ones we just produced. Today, I'm going to be applying a very general fermented plant juice to these pineapples. First, we're going to start by mixing our solution. Our dilution rate is going to be 500 to 1. So for this 2-gallon sprayer, I'm going to be adding about 15 milliliters, which is about 2 teaspoons. Now when we're applying our fermented plant juices, we want to make sure that we're going to spray the solution on the top parts of the leaves and also on the underneath, trying to get to the stomata, where it can be absorbed into the plant tissue. We also want to make sure that we get it near the root area, so it can be absorbed into the plant that way. And that's field application of fermented plant juices. It is recommended that you apply fermented plant juices at least once a week if you're a commercial farmer. Lactic acid bacteria is a cladobacteria, which is known as a beneficial probiotic microorganism that exists in the gut of many animals, as well as exists in several plant structures. It is also the end result of carbohydrate fermentation and is responsible for the prevention of spoilage in foods like kimchi or sauerkraut. Lactic acid bacteria, or LAB, is very tolerant of acidic conditions and can decompose sugars very quickly. In the soil, LAB will trigger rapid decomposition and mineralization, which can unlock plant-available nutrients in the soil. When diluted, lactic acid bacteria can be used as a plant foliar spray, which can increase the water-holding capacity of your plant, improve cell wall structures, and prevent infestation of pathogens. It is also very useful in livestock production, as it can prevent odors and insects from entering your production area. Now let's learn how to make and use this amazing natural farming amendment. For lactic acid bacteria, you will need a measuring cup, 3 cups of dried white rice, a ½ gallon of fresh water, a ½ gallon glass jar with a lid, paper towel, tissue paper, or some cloth, a rubber band or some wire, a large metal strainer, a ½ gallon of milk. Non-pasteurized is preferred, but you can use pasteurized milk. A 1 gallon container, and finally, 2 cups of brown sugar or turbinado evaporated cane juice. Now we're going to make lactic acid bacteria. First, we're going to do a very simple process of getting lactic acid bacteria off of this rice and into an aqueous solution. So what we're going to do is we're going to put a little bit of water in about 3 cups of rice. We'll put a top on that jar. Shake it around real good. And what we're doing here is we're getting the bacteria that's on the rice into the water. Of course, we're going to get a little bit of other things like carbohydrates from the rice and proteins. So now we have what we call rice wash water. And that's going to be a very milky solution after you've stirred up rice and water for just a little bit. Next, we're going to want to separate the rice from the rice wash water. Next, we're going to take a permeable layer and put it right up over top. Cover it with a permeable layer. I use a t-shirt. You can use a t-shirt, piece of cloth, paper towel, tissue paper, anything that has a permeable layer. The t-shirt is nice because it protects the jar from direct sunlight because of its size. We're going to put a wire around, a rubber band. And we're going to leave this jar in a cool, dry place for 5 days. We'll go ahead and check on it, and then we'll use this to make lactic acid bacteria. Now it's been 5 days since we put our rice wash water in a cool, dry place that did not get any sunlight. And let's go ahead and take back the permeable layer and take a look at the stratifying layers that have happened over the course of 5 days. What we have here is proteins on top. We have our lactic acid bacteria, which is on the inside, in the middle of the layering. And then we have our carbohydrates and sugars below. Now what we're looking to do is actually get the materials from the middle, the liquidy materials, into a food source. The food source, in this case, being lacto. This is coming from this unpasteurized milk that we have here. You're more than welcome to use pasteurized milk, it does work. But you're going to get a lot more microorganism and a lot more metabolic activity in unpasteurized milk. So then what we're going to do is separate the solids from the liquid by using a metal strainer, like this one here. placing it right up over top, and then just pouring the materials in here until we fill up this jar just about below the lip. Now that lactic acid bacteria, which was in this jar, has a food source, which is lacto, which was in the milk, we're going to allow this to sit for 5 to 7 days and allow another session of stratifying layers where we're going to get cottage cheese on the top and whey, which is going to be our lactic acid bacteria solution in the middle. So after 5 to 7 days, we'll check on it. We'll cover it up with this permeable layer in the meantime, which will allow for gas exchange. You can use paper towel, you can use tissue paper or a piece of cloth. I like to use the t-shirt because it prevents direct sunlight. So let's come back to it in 5 to 7 days, and we should have curds and whey. It's been 7 days since we put our rice wash water and our milk mixture into a cool, dry, dark area. And we're going to go ahead and take a look to see if we've been able to make some lactic acid bacteria. Now what we have here is wonderful layers showing the protein on top, the lactic acid bacteria in the middle, and then the carbohydrates on the bottom of the jar. Now, the goal here is really to get to this yellow liquid in the middle. The cheese that is on top can be fed to your livestock or consumed personally, or just go ahead and throw it away. And then you're going to want to make sure that you get all of this yellow material into this jar. So let's go ahead and scoop off the top. I like to use a spoon. Let's go ahead and pour this liquid into this jar. Now this lactic acid bacteria, which has been given energy with the lacto from the milk, is going to need a little bit more energy to sustain itself on the shelf. So what we use is about 1/2 cup of sugar. We'll go ahead and put that right into the jar. You can use evaporated cane sugar as well. But as in all natural farming methods, you're going to want to use the dark brown sugar. Go ahead and put a lid on the top. Shake it up. And now we have lactic acid bacteria. Now this is going to be used in the field as a foliar applicant to combat fungus, bacteria, also insects. This truly is one of the best concoctions that you can make for natural farming. This is lactic acid bacteria.
So it doesn't need to sit after you add the sugar, in that case it's ready to work.
There you go.
So there are bacteria or microorganisms can be found just about anywhere, soil, plant surfaces. The application of, say, the inoculation of bacteria or microorganisms is not limited to the inoculations of it in the soil. You can also inoculate on the plant surfaces. In fact, some of the leaf surfaces are sprayed or inoculated with, say, teas, water extracts from compost teas or vermicompost teas or whatever extracts you have. And the theory behind it is that when you inoculate plants with these teas with microorganisms in it, to protect the plants from being attacked by other microorganisms that may pose pathogen to the plant. Again, the theory behind or the mechanism behind is hyperparasitism. The plants, some of the bacteria or fungal will feed on plants that are already existing on the plant by extracting whatever the sap that they have extracted from the plant. So that mechanism behind is hyperparasitism or parasitism itself, because they live on other organisms that already live on the plants. So, and this is the theory behind spraying the plants with water extracts from plant extracts or compost, that is. If there is a pathogen in the soil, and then you inoculate other microorganisms into the soil, there are many things that could happen. Some microorganisms can act as an antibacterial for the pathogen. If the pathogen is a bacteria, there are pathogens that are antibacterial. There are microorganisms that feed on bacteria, for example. So the way they manage the population is by competition. So they competition for space, competition for essential elements. These, the microorganisms that may act as pathogenic, again, will be defenseless because they're outnumbered. Some nematodes, for example, in the trophic level are fungivores or bacterivores. And if these pathogens are fungi or these pathogens are bacteria, very easily their numbers will be down because you are encouraging other microorganisms like nematodes, because nematodes are not all parasitic, they're not all plant parasitic. There are a large population of nematodes that actually feed on bacteria. And if they are in great numbers in the soil, then they can outlive and they can actually feed on pathogenic bacteria or pathogenic fungi. There are also a group of microorganisms that are that produce antibacterial metabolites and antifungal metabolites. And so they may not be eaten or competed with in terms of they're not being competition in terms of space and nutrition with pathogenic microorganisms, but their metabolites can act like antibacterial or antifungal for these pathogenic microorganisms. That's why there's really there's an emphasis on increasing diversity in the soil, because all these antibiosis, antifungal, and maybe even systemic acquired resistance for plants can be enhanced by the presence of a lot of diversity in microorganisms.
But systemic acquired resistance is a real thing. You can have a plant and inoculate it with a fungus that doesn't cause a disease necessarily, or a bacteria that doesn't cause a disease necessarily, right? But when you inoculate it, that sort of stimulates something, and then you get this acquired resistance thing. And then people have shown that really has a protective effect on for these plants. So that you might inoculate with a fungus that doesn't cause disease, and then nothing happens, right? But then you come in and you try to inoculate that plant with a pathogen, and you will see hardly any disease.
Next, I'm going to be introducing lactic acid bacteria. I'm going to show you how to dilute it and apply it both in the field and with your livestock. We're in this natural farming piggery designed by the University of Hawaii in Manoa, and we're going to show you how to apply this with a set of pigs. First, we're going to use lactic acid bacteria to inoculate the feed of the pig. This is going to increase the beneficial bacteria and probiotic bacteria that are on the inside gut of the animal, improving the health of the animal. We're also going to spray it on the outside of the pigs. In case there is any fungi or bacteria that are stuck to the sides of the pigs, it might cause smell or odors in the piggery. We're also going to apply it to the floor in the deep litter system so that it will help break down organic material left over by the pigs. This system can be used with cows and chickens as well as pigs and pretty much any other livestock. So let's go ahead and dilute some lactic acid bacteria with our water at a dilution rate of 500 to 1. This is easily converted into about 2 teaspoons per gallon. I have my 1 gallon sprayer. I'm going to add 2 teaspoons. Go ahead and apply it to the food, to the sides of these piglets, and then a little bit to the floor. After that, we'll go out to the field and use the lactic acid bacteria as a fungicide as well as a pest deterrent.
So this is the piggery I'm going to bring the group to. Notice the pigs are making a noise. You know anywhere, any other piggery you can film in? I don't know of one that you can sit in without the pigs squealing and yelling at you. Those are extremely happy pigs right there. A little bit sprayed on the feed. You can use, most of the time we feed these pigs sweet potato, just chopped up sweet potato, so just spray right on that. All set. So the big one will come over to the fence if it knows that I'm spraying this to get sprayed because it knows it feels good after it's done. Gets rid of all the itch, flies, pretty much drain the pig into the lactic acid bacteria.
Once a week?
Yeah, sounds good.
So one batch lasts quite a bit.
An incredibly long
As long
time.
as you don't have a big.
All of the amendments I talk about, these production of these amendments, if I had my own property, I would do one.
As you can see, lactic acid bacteria has a wide range of uses.
It's not like you have to
Let's go out into
produce
the
this all
field and
time.
use it as a fungicide and a pest deterrent.
Yeah, so you can spray foliar with it as well.
Is that coverage?
Yep.
Fish amino acids, or fish emulsion, is a natural farming amendment made from fish parts, which is high in nitrogen, potassium, calcium, magnesium, and phosphorus. Sugar is used in producing FAA, or fish amino acids, because of its osmotic properties, its ability to leach nutrients out of the fish material. This basically makes fish amino acid a soluble and effective plant nutrient source. When this material is diluted, it can be used to make IMO4 or used as a foliar applicant for plants or a foliar spray on soil. Natural farmers also use this material as an insect deterrent. Now let's go ahead and learn about this effective and simple natural farming tool. For fish amino acids, you will need 4 to 6 pounds of fish waste materials, 6 to 10 pounds of brown sugar or turbinado evaporated cane juice, 2 5-gallon containers, preferably clay or stone, they can be plastic, paper towels, tissue paper, or cloth, rubber band or a wire, a large metal strainer, a 1/2-gallon glass jar with a lid, and finally a cool, dry, shady area. We can start off the fish amino acid process with the simple materials that we have here in front of us. First, you're going to need a container, We recommend clay or terracotta pot, just like this one here. You can use plastic, but the clay or terracotta is strongly recommended. If you're going to get a pot that was used as a potted plant, we recommend you plug up the bottom. I used a plunger and a little adhesive or whatever means necessary to make sure that the vessel can hold liquid. Okay? We're going to have fish waste here that we've collected from our local fish market. We collect fish that are going to be blueback fish. These are going to be the large predatory fish like tuna and salmon. And this is where we're going to get some really good nitrogen and amino acids from. This process, we start off. I like to protect my hands only because this could be a stinky process. And I'll take a little bit of material, fish material, I'm going to lay it onto the bottom of this pot here. So here we have innards, we have heads, we have fins, and this is all freshly caught this morning, and I was able to get it from the fish market and bring it out for this process. So, once I put a nice layer of fish on the bottom of the pot, like so, I'm going to go ahead and scoop out some sugar. And I'm going to create a layer of sugar that is so thick that I cannot see the fish material anymore. Now, as in all the other natural farming processes, we like to use dark brown sugar or golden brown sugar, definitely not white sugar. Turbinado, evaporated cane sugar works great as well. Push it down real good. Now I'm going to put another layer of fish on top. The goal here would be to make 2, if not 3 layers. This pot only allows me to make 2 layers. Just enough fish there. Sugar right up over top. As you can see, it takes several pounds of sugar, so you want to make sure you have plenty of material for the fish amino acid process. So we have our pot full of fish and sugar. The sugar in this process is going to do the same thing as in the fermented plant juice process, where we have osmotic pressure, which is going to pull out the nutrients from the fish material. It's going to pull out the nitrogen, it's going to pull out the amino acids and proteins, and then it's going to liquefy it into a solution. So we're going to cover it up with a permeable layer, like this old t-shirt here, which allows airflow, but these flies and other bugs do not enter. You can use a rubber band or a wire.
Rubber band works a lot better than wire, keeps flies out. Wire works best pretty much.
Place it right around top. Twist it off,
Zip tie might work great.
and we have
Yep.
our pot for fish amino acids. Now, we're gonna let this sit for 7 to 10 days in order to get the liquefied fish matter. And like I said, you could let this sit for 6 months and it will continue decomposition. Eventually, all of the materials would turn to liquid and be available to use as a plant nutrient. And that's fish amino acid. So it's been about 10 days since we took our fish and sugar and put it into this pot. Let's go ahead and take off the permeable layer and see if we got some fish amino acids. What we're looking for here is, of course, the liquid, and which is full of nutrients from the fish flesh caused by osmotic pressure from the sugar. And of course, we have some microbial activity, which is pretty obvious from the bubbles on the top of the liquid. What we're going to do next is we're going to filter this into this 5-gallon bucket with a 1/2-inch graded screen. We'll go ahead and
Want to know where to get fish guts and stuff? Go to Suisan before 10 o'clock, between the hours of 9 to 10 o'clock. They have all of their trash cans full of guts, heads, and what have you. Let you pick through it and take out what you need. I go out there once a week, they know me by name. You don't have to tell anybody you're there. They put it right on out. You just walk on out. Make sure you have a nice bucket. Make sure you got rubber gloves. And find what you want and don't make a damn mess. Because they won't let you come back. But you can get out there and get as much of this material as you want.
now we're left with,
You don't need to buy
of course, fish pieces that have not broken down. And what I would typically do is go ahead and add about 3 or 4 pounds of sugar to this pot, cover it up with the permeable layer, and allow it to sit for an extended period of time.
You grind
Because
it.
there are still materials in this fish,
But then you'd have more
guts,
surface.
bones,
Yeah,
and
it
flesh
would work,
that
but
can be used to make fish amino acid over the next few months. So, this
the
pot
bones aren't going to break down any faster. It's still going to be bits
is full of our
bone
fish
as
amino
opposed
acid.
to
Let's go ahead and put that into a jar.
spine. It still needs time to break down.
Why terracotta instead of plastic?
Just because it's just more recommended because of the holes that are in the terracotta allow for a little bit more oxygen to be available for decomposition. I use plastic buckets.
No, this is the smell.
You're going to want to go ahead and cap that off. But you're going to want to make sure that you have plenty of airspace in here because of the microbial activity that will continue in the fish amino acids. Now, of course, this is used as a nitrogen source for your crops and can be used to make IMO 3 and 4. This is fish amino acids.
The economics of
So that
natural
you guys can see
farming
IMO 4, I'm going to fast through to the science.
is very, very, has a very high potential of reducing chemical inputs.
So we want to use all of these, right? The lactic acid and.
Oh, sure, and then there's
Use them all.
about 10 more that aren't in the video.
So as many options as possible, just keep mixing it up.
No, everyone has its purpose and its use, you know.
Well, depending on what's going on.
As long as you have to understand what each one's for and then use it for its specific use.
A pump sprayer, like the one below. And then we're going to have our concentrated fish amino acid. Simple process of mixing the fish amino acid with a little bit of water to dilute it by a 1 to 1,000 ratio. Basically the way that works out.
Got that? 1 to 1,000. Just like the lactic acid bacteria.
4 teaspoons.
No, 1 to 1,000 would be 1 teaspoon per gallon. 1 to 500 would be 2 teaspoons per gallon. So you just essentially spray it the same way foliar spray. But make sure you hit the root base as well. You want to make sure you hit the root base as well.
Natural farming. One of the most widely used and effective natural growing tools is IMO4. This soil inoculant is used to increase the beneficial microorganism populations and biodiversity of your soil. Unlike most soil inoculants, IMO4 utilizes site-specific microorganisms that have adapted to each farm's microclimate. These indigenous microorganisms are cultured from the immediate environment. They're used to ferment some plant-based materials, and then are quickly composted, utilizing some unique natural farming techniques. After that, the material is applied into the field as a soil inoculant. When producing IMO4, farmers only use plant-based and animal-based products to produce IMO4. Many of the ingredients used in IMO4 production are agriculture byproducts and waste materials, which actually makes IMO4 one of the most cost-effective and sustainable soil inoculants available. Most natural farmers that consistently use IMO4 soil inoculant have seen an increase in crop yield, crop water holding capacity, a significant decrease in the need for added plant nutrients, a decrease in plant pathogen occurrence, and an overall improvement to plant and soil health. I will now show you the 4 steps of IMO4 production, starting first with IMO1, then IMO2, IMO3, and then eventually our end product, IMO4 soil inoculant. For IMO1, you will need a wooden box, 6 to 10 cups of steamed white rice or breadfruit, paper towel, tissue paper or a piece of cloth, wire mesh, a spoon or a rice paddle, a staple gun or rubber bands, and plastic sheeting. We're going to start the IMO process with making IMO1. IMO1 is started in a wooden box just like this one here. I recommend using cedar as it has terpenoids in it, antimicrobial properties. And the dimensions of the box, I recommend 12 to 18 inches in width and 12 to 18 inches in length, and then about 4 to 6 inches in depth. We're going to then place a sterile media inside this box to collect our microorganisms onto. I'm going to use rice for this round. You can also use breadfruit or any other starchy material that has been steamed and sterilized. Here's my white rice. I want to make sure that your carbohydrate source, your sterile media, has aerobic conditions. Basically meaning that air can flow between the material very easily, and microorganisms that are dispersed through wind can actually pass from one rice kernel to the next. So I'll fill up the box just like so. I'll make sure I flatten out the rice in an effort to put 3 inches of rice in every section of the box. Now, we have our rice media here. We're going to want to cover it with a permeable layer, and I tend to use paper towels, just like these here. Place them right up over top, and what we're doing here is we're separating the organic materials that we're going to gather our microorganisms from our sterile media. Next, we're going to want to prevent any mammals, rats, mice from getting into the box, so we're going to cover it with a metal grate. Recommend the metal grate fits closely in dimensions to the box, and then we're going to recommend at least a 1/2 inch square. Do not use chicken wire, as the mice can actually go in and out of the chicken wire. We're going to secure it down with a heavy-duty staple gun, like so.
If you don't have rats or mice problem, you don't need to do this step. I don't know anybody who doesn't.
Now our sterile media is secured into the box. We're going to then go gather some microorganisms from the forested area around the agriculture area, place them on top, and secure them nicely. So we'll go ahead and gather those microorganisms now. Now when we're culturing indigenous microorganisms, we're going to want to culture them from a shaded area similar to this, in an area where there is no direct sunlight and a lot of decomposition. So we're going to go ahead and culture in this banana patch, just like we did under a few other areas of decomposition. First, we're going to go ahead and pull back the first layer. We're going to look for decomposing material, bacteria and fungi rich, maybe a little bit of the topsoil. Be sure you wear protection on your hands, because you never know what's in this material. We have our indigenous microorganisms. We're going to go place it on our sterile media and go from there. Now that we've cultured some indigenous microorganisms, we're going to take this material and put it over our sterile media in our box. Now the goal would be to have these fungi and bacteria reproduce onto the sterile media. And we're going to stimulate that by changing the conditions of the microorganisms and how they currently exist. So we're going to take this material and place it up over top, just like so. Now, the reproduction happens above, and then the spores that are released from the microorganisms will be released onto the permeable layer and then transfer onto the sterile media below. Now, we need to cause these microorganisms to reproduce, and we're going to do that by changing their condition, like I said. Place a plastic tarp up over top. You can use clear, colored plastic. Either way, you're going to want something where it's going to trap the heat and trap the moisture in the box. I'll take a staple gun, staple around the side. You can use a rubber band to secure the tarp, but you want to make sure that there's plenty of airflow in the area. So with a rubber band, sometimes that can prevent airflow. So I recommend staple gun. So then this material is all covered in the plastic. It's going to be high moisture, high temperature in here, and then those spores will drop onto the sterile medium. We're going to take this box now and place it into the environment in which we got this material. And then we'll come back and check on it. To finish off IMO 1, we're going to go into a dark, shady environment like this banana patch here. Place the box directly onto the soil, and then we're going to cover it up with leafy material from the environment. We do this so that in case there's any breaks in the trees, and no sunlight can actually penetrate into the box. So we want to leave that there for 7 days. After that, we'll be able to use it to make IMO 2.
So if we think about
really good stuff there too. But we'll get out of here at 6:30 if I don't fast forward.
Juice. A 5-gallon container, preferably clay or stone, or it can be a plastic bucket. A long spoon, paper towel, tissue, or a piece of cloth. Rubber bands or wire. And a food scale with at least a 6-pound maximum. Now we brought our IMO 1 box out to the agriculture area to make IMO 2. To make IMO 2, you're just going to need the IMO 1 box. You're going to need a clay, terracotta, or stone pot. I used a clay pot and put a rubber stopper and adhesive in the bottom so that it holds liquid. You're going to need a food scale similar to this one here. Now what we're going to do first is we're going to take back the plastic off the top of the IMO 1 box, and push aside the organic materials so that we can expose the permeable layer.
If you don't have a scale, eyeball it. It's what most people do.
So here we have our permeable layer which stands above our rice media, and then the cage over top. So what you're going to do is pull back the cage.
Don't do this in your driveway.
So that we can get to the material below.
Put staples in your tires and you wonder where the heck those came from.
So here we have a diversity of microorganisms and macroorganisms inside the box, a couple ants and some grubs, and most importantly, we have our microorganisms which have dropped down to the top of the permeable layer. Let's go ahead and pull back that paper towel and expose our rice media.
What a great culture. Look at that. That was one of the best cultures I ever did. It was for the film, so that was pretty good.
So here we have our rice media. It's basically full of a whole consortia of microorganisms, from the white cotton candy-like mycelia to the pinks, the grays, the peaches, some greens, obviously a nice collection of indigenous microorganisms. We're going to take this material and put it into this pot. We're going to measure the weight of the rice and microorganisms, and then add sugar, which is going to give a carbohydrate or energy source to the microorganisms that we're going to use in the next phase of IMO4 processing. So what we're going to do first is weigh this material. I know this pot weighs 15 pounds, so let's go ahead and weigh the rice material in addition to the pot. Now you're going to want to break this material up as much as possible as you're putting it in.
Essentially, each kernel turns into a seed.
Now I have to say, you can't feel it at home, but this is actually very, very warm. This rice material is about 120 to 130 degrees right now. And that's because a lot of metabolic activity going on in here, and microorganisms are just moving all over the place, causing friction, which is where the heat comes from.
You don't need to do a batch this big. I just do a batch that big because I make a lot of IMO. You can do one about half the size and totally be fine. But the more you make now, and if you store it correctly, you don't need to make it ever again. So that's enough IMO too to last a couple of years. You only need to do it once in a couple of years. People think you need to do this, like make these things all the time. No, you make it a couple times a year and then you're just a natural farmer.
Now, the scale is going to go ahead and indicate to me that there's about 10 pounds of rice and microorganisms in here. So I'm going to go ahead and add equal weight of sugar.
Which is about 3.5 pounds more than there was before when I put the rice in, which means about 3.5 pounds of microorganisms in there.
Now, as in all natural farming methods, you're going to want to use dark brown or at least golden brown sugar. You're not going to want to use white bleached sugar, and you can also use turbinado cane sugar, which is evaporated cane sugar.
Cane sugar, sugar.
Ideally, you wanna grow it on your land, right?
But yeah, you just get some sugar cane and then you juice it and put it out in trays in your greenhouse, let it sit for about 2 days, and you get just a lot of sugar. How much do you really need for this? Well, to produce enough amendments for 2 years, maybe 50, 60 pounds.
There, we got a full pot,
That's maybe
10 pounds of rice material,
50, 60 gallons.
and we have 10 pounds of sugar. Now go ahead and take that down.
Or you just suck it up and go buy it.
The next thing I'm going to do is mix this with my hands. I'm going to want to get all that sugar coming in contact with the rice media below. So this is the first steps of the IMO2 process. Basically what I've done, like I said, is add a carbohydrate source, a food source, and given it to the microorganisms that are on the rice media. This is going to allow them to ferment, and over time it's going to become a very soupy, liquidy material. Now, the time period is going to be 7 days, which is going to allow us to ferment this material long enough so that these microorganisms have plenty of energy to spread onto the IMO3 media. Now, first thing we're going to do to make sure that it ferments properly is cover it up with a permeable layer. I use an old t-shirt. Seems to work the best for me. You can.
Fast forwarding t-shirt, wire, keep things out, let things breathe.
And by putting them separately.
Run. Rice bran, sugarcane bagasse, or breadfruit flour. You will also need fermented plant juices, fish amino acids, a long spoon, a 15 to 30 gallon container or several 5-gallon buckets, a shovel, straw mat or local grasses, a composting thermometer, and finally, a shady composting area with a soil surface. So now we're ready to make IMO3. It's been 7 days since we took our rice material, mixed it with sugar, and allowed it to ferment, giving it plenty of energy for reproduction. Now we're going to use that IMO2 material to mix with our carbohydrate source. Today in our carbohydrate source, we're going to be using wheat mill run, which is an agriculture byproduct of processing wheat. You can use any other carbohydrate source, just like sugarcane bagasse or breadfruit flour, which works great. You're also going to need some diluted solutions. First, we're going to talk about our fermented plant juices. That's going to be diluted at a rate of 500 to 1. And then we're also going to use a nutrient solution, and I prefer to use fish amino acid. That will be diluted at a rate of 1,000 to 1. To start off with, let's mix some IMO2 with water. To start off the IMO3 process, first let's check on our IMO2 rice material. What we have here is rice material fermented with sugar, inoculated with indigenous microorganisms, which is full of plenty of energy, and they're ready to reproduce. So what we're going to do next is mix this a little bit of water to make an IMO2 solution. Now the amount of IMO2 that goes into IMO3 is certainly debated. Some folks will actually use the entire bucket and use that to inoculate their IMO3. Some folks will use just a very, very small amount. I prefer to use about 3 handfuls per 5-gallon bucket. So let's go ahead and pull out 3 handfuls and mix it with our water.
John Caverly, the guy who owns the farm we're filming this on, he uses a pinch. Just a pinch. And he gets some great inoculation. Actually, sometimes he doesn't even have to inoculate because his floor is so inoculated from so many batches that he can almost skip over this stuff. Yeah, he stopped culturing from the environment, he cultures from his IMO bar.
Now this solution will be used to mix with our carbohydrate source. So now I have my carbohydrate material on a soil surface, and I'm going to go ahead and make a nice little hole in the middle of the pile.
Stuff's very dense, very powdery. You almost need that, which is why sugarcane
Just like that.
work as well.
This is going to be a
There's
great
lot of
place to
space
go ahead and put
between
our
the
solutions
material.
into, and allows us to mix it without the solutions running about. So let's go ahead and grab our IMO2 and put it into our carbohydrate material.
How much is that? How much carbo?
There is 180 pounds right there, 360 pound bag. Minimum, you want to do 60 pounds.
We can put about half the bucket.
Some say minimum, you want to do 120 pounds. I would agree with
We'll go ahead and start mixing. I like to bring the outside inward into the pool in the middle.
I made 12 of these in one day last week.
So you bring in this winter?
Yeah, well, they weren't there. Usually I do, and they weren't there. And you gotta know, it's material like that, like with flour, you know, the more liquid you add, the more harder it is to work with. So really getting the microorganisms spread throughout the
Now that we
material
have it
before you start adding moisture. is
somewhat
key.
mixed, we're going to want to make sure that we make our IMO3 the right moisture content with our solutions. We're looking for a 70% moisture content. And you can judge this by squishing your material together, and if it holds like a snowball, you're about 70%. So let's go ahead and add those solutions and see if we can get the right moisture content. Fermented plant juices. And let's add the rest of our IMO2. This is our second bucket.
That's just water, just water?
This is fish, this was fermented plant juice second bucket. We've only put in the IMO2 and the fermented plant juice so far.
Now let's add some fish amino acids.
So funny when I was filming this, man. After a while, like, I'm so soaked with sweat and like, just exhausted. The sun's going down, the cookies start going out. Shows how long I was there. I think I started filming this at 2, and the cookies were coming out by the time I was done.
How many gallons do you think the plant juices in the fish?
10 gallons each, and then supplement the rest of the moisture with just fresh water.
Good.
I got a cement mixer.
Yeah, right?
Not recommended. It's really not. because it turns to paste, and I swear it's so much harder to work with than if it's
So
just
that's
on
the last of
floor.
our solution.
I've been there before.
We're still gonna need a little bit more moisture. So let's go ahead and add some fresh water.
Need woofers.
You're walking a little stiff now.
I've been bending over for an hour.
We're about halfway through the stirring process. Let's go ahead and check the moisture.
That's what I'm saying, look at that.
Like I said, the material should
Is it
stick
raining out?
together like a snowball, and it seems to be falling apart still, and still kind of flaky. The more I squeeze, it still doesn't hold on. So let's go ahead and add a little bit more water, anywhere between 5 to 15 gallons. So now we've mixed our IMO3 with our solutions and
Hey,
water.
tripod.
Let's go ahead and check the water content one more time.
That's community college television right
Pull out a
there.
little sample, squeeze it in your hand. And if you could make a nice solid ball like this, you have the right moisture content, which is right about 70%. You can tell if you have the right moisture content by pushing on it with your finger, and if it falls apart easily, then we're at about 70%. So next, we're going to take this pile and lay it out in a square shape or a rectangle shape at about 12 to 18 inches in height.
Make a kid single bed, basically. 12 inches, nice square, rectangle shape.
Look like you slept good that night.
No, because I didn't do it again the next day probably. I make like 3 batches of this a week.
Now that this IMO3 pile has the right moisture content, it's also the right shape and the right height, we're going to go ahead and cover it up. Now it is recommended to use natural grasses, a grass mat to cover it. You can also use a sheet, canvas tarp, or anything that will prevent sunlight from hitting the pile. Let's go ahead and grab this drop cloth and put it over top.
Cardboard works good. If you're out in the environment, cardboard. But make sure that the material's not too moist if you use cardboard, because it will trap the moisture in.
Now that we've covered our IMO3 pile, placed it on a soil surface, and made sure to protect it from meeting direct sunlight, we're going to monitor this pile very, very closely over the course of the next 7 days while it is fermenting. The reason is temperatures in this pile can reach 130, 140, sometimes even 150 degrees. We're going to monitor this very closely with a composting thermometer and then stirring it regularly to maintain the temperatures desired. Now these temperatures are high enough to kill off any pathogens that may exist in the pile. And it will also enable us to culture out and isolate beneficial microorganisms that exist within the pile. So in about 2 days, let's come back and check the temperature and see if we need to stir the pile.
You went to Harvard. You can tell.
White fungus on the top of the pile. This is going to give me an indication that there is a nice inoculation into the pile. First thing we're going to want to look for in our IMO3 pile, of course, is the mycelial mats and wonderful white fungus on the top of the pile. This is going to give me an indication that there is a nice inoculation into the pile, and we're going to have plenty of reproduction and microorganisms spread throughout the material. Next thing we're going to want to do is going to check the temperature with a composting thermometer to make sure it has not gone over 130 degrees.
Oh, I just realized I fast forwarded over your materials list. You want to see that?
Do we have materials yet though? We're still checking after 2 days.
Oh, I think I'm.
130 degrees.
Right. We'll see. If not, I'll go back.
So I placed the composting thermometer into our IMO3 pile, and it's giving us a reading of about 131 degrees, which is just over what we're looking for as far as IMO3 processing. So what we're gonna do is we're gonna go ahead and stir this pile so that we can release some of that heat and also give an opportunity for the microorganisms to spread to different areas of the pile. Next, we're gonna mix our IMO3 pile. The goal here would be to fold the material over itself and try to bring the material that's on the bottom towards the top of the pile.
You see, it has like a hard shell on the outside. Yeah. The goal is really to get that hard shell on the inside.
Now that we've stirred our IMO3 pile and laid it out at the specified height of about 12 to 18 inches.
After this one, I made the photographer stir them after I stirred it for about 3 minutes because I was too tired to film last time. I'm like, all right, you do it.
We're gonna go ahead and cover it up with our tarp.
Like, I'm paying you plenty of money. You can stir it. How unsweaty I am.
And what we'll do next is check on it every day between now and the end of the fermentation process, which is 7 days from the original making of the IMO3. We want to make sure, once again, that the temperatures do not reach above 130 degrees, and then we'll maintain those temperatures and the height of this pile until we're ready to make IMO4. For IMO4, you will need at least 50 pounds of local soil, 15 to 30 gallons of fresh water, fermented plant juices, fish amino acid, a 15 to 30 gallon container or several 5-gallon buckets, a shovel, some straw mat or local grasses, a composting thermometer, a shady composting area with a soil surface, and if available, 1 gallon of seawater. Now what we're looking at here is a finished IMO3 product. We know it's finished first of all because of its color and the sheer amount of mycelia that are in the material. We also know that it's finished because we've been stirring it every day, monitoring its temperatures as it reaches 130, 135 degrees. And then slowly and surely those temperatures started going down to 120, 115, eventually 110 degrees. This started giving us a good indication that the metabolic activity of the microorganisms in the material are slowing down and they're looking for a new food source. So what we're going to do next is going to mix this material at a 1-to-1 ratio by density with local field soil or compost. This will then allow us to create IMO4 that we can use to inoculate our field.
What is compost?
So I've been able to thoroughly mix my IMO3 with some field soil at a 1-to-1 ratio by density. I've also been able to create a nice divot in my IMO4 pile so that when we lay in our solutions, they're not going to leak up over the edges. For our solutions today for IMO4, we're going to be using fermented plant juices diluted at a 1-to-500 ratio with fresh water. We're also using fish amino acids diluted at 1-to-1000 ratio with fresh water. And we're also going to be using a little bit of seawater diluted at a 1-to-30 ratio with fresh water. Now the seawater is going to create slightly sodic or salty conditions, which will make it difficult for any pathogens that still remain in our IMO3. Now, we're going to add these solutions in, looking for a 70% moisture content, just like we did in IMO3, and then we'll check it periodically as we are dumping these solutions in. So let's go ahead and mix our IMO4.
Yeah, about 5 gallons of the diluted seawater.
Diluted 30-to-1?
30-to-1, yeah.
So I've successfully been able to mix my IMO3 with field soil, also with the solutions. And next we're going to check the moisture content of our IMO4. Just like with our IMO3, let's go ahead and take a ball of it, squish it up into a round shape. And if it holds its shape after releasing and crumbles apart by pushing on it with your finger, you're at about 70% moisture content, which is just perfect for IMO4 production. Next thing we're going to do is, of course, cover the pile to make sure it stays out of direct sunlight. And we'll be sure to check on it every day, just like we did our IMO3, to make sure that the temperatures do not go above 130, 135 degrees. We'll go ahead and stir it once a day, and then come back in about 7 days. The fermented The temperatures should be evening out at about 110, 105 degrees, basically indicating metabolic activity is slowed down and the IMO4 is ready for application in the field. Let's go ahead and take a look at the temperature right now. So the temperature gauge is basically indicating that it's about 105 degrees and shows that the finished product is ready to go into the field. Now for storage of our IMO4, you're going to want to make sure it stays in a cool, dry area away from direct sunlight, just like your IMO4 production area. You're going to want to bag it in a permeable bag, similar to an onion bag, that has plenty of airflow. Now we're ready to go ahead into the field, take our IMO4, and place it next to our crops. Next, we're going to apply IMO4 into the field. To show you how to do that, we're going to use this coffee tree as an example. It has about 6 square feet of area at the root base, and we're going to clear off this area to start off our IMO4 application. First, we're going to take all the leaf matter and the weeds and move them aside and remove them from the area. And then we're going to apply our IMO4 at a rate of 150 pounds per acre at the base of the tree. With a 6 square foot area, that comes out to about 2 handfuls of IMO. Next, we're going to take our mulch and place it up over top of the IMO to protect it from sunlight and allow it to do its metabolic activity and biological processes without being interrupted by sunlight. So first, let's look at the base of the tree, which has already been cleared off. And next, we're going to place these 2 handfuls of IMO near the base. We're gonna scatter them evenly to the 6 square foot area and then finish it with mulch.
You already said that, dude.
As you can see, it takes a very small amount of IMO to inoculate the soil at the root base. And that is it. We've just inoculated this tree with IMO 4. You're going to want to do this maybe once or twice a year, and that would be enough to make sure all those beneficial microorganisms have inoculated the soil beneath.
Anytime you create a healthy soil condition, anytime you apply the right nutrients in order to have the soil microbes do well in, oftentimes you're going to have.
Do you want to finish it or are we done?
It's a very normal thing to think about. If you have things that are doing well.
Talks a little bit about wrapping up some of the science, and then it talks about a call of action, like to folks to get out there and do something about it, get some research done, and that's about it. So, did you get a good introduction to natural farming today? 6 hours worth of exposure, a bunch of film, all that stuff? Good. Do you feel like you learned something?
Oh yeah.
Okay.
It's a lot of work though.
Yeah. So you see it's an option, and feel free to partake in the community, and even if you don't make your own amendments and you think it's a cool idea, I think you should show up to the meetings and support the community and show up next week and all that stuff. So, let me sign any of these wonderful certificates. Is Amy still here?
Yeah.
There we go. Vanessa. Hold on to Gino. James?
Thanks, man.
Lonnie? Still here? Took off. Okay. And we'll send you one as well. Any questions?
So next week, what does it look like? Is it doing all that stuff that we saw, or is it?
Yeah, it's I'm gonna have a pile of IMO 3 kind of ready to go into IMO 4 so you can see it done. We'll probably make a pile of IMO 3, some lactic acid bacteria and some fish amino acids, and we'll do fermented plant juice, probably some water soluble calcium. We'll put it out in the application. It's just more of a hands-on how to make them. So you got formulas here. I've never found anybody that can take a formula from a written or a visual and actually reproduce it. But you'll be ahead of the game when you show up next week for that. So I strongly recommend.
Do you think you'll still wait to hear if it's gonna happen?
Monday at noon. If I don't have an okay, then I'm not going to. So make sure I have
Yeah,
all
we have
forms.
ours. Yeah.
Everything's here
So
or
Rachel,
here. Okay.
You get emails.
So I would assume it's gonna go forward. I don't know, just call my office if you haven't enrolled, ask them if it's gonna go. If you've already signed up, maybe chime in.
And is, would the class be meeting here first in this classroom, or?
Yeah, we'll meet right here, and I'll probably just do attendance and that kind of thing. Ask if anybody got any questions, and then we'll head over to the back.
Thanks.
No worries.
Men's room?
Yeah, right around this way.
On the right, keep on, or?
It's beyond the green fenced-in utilities, just on the other side.
Thanks again.
Yep.